테스팅 하나 둘 테스팅 하나 둘 테스팅 이거 잘 쓰시더라고. 테스팅 하나 둘 볼륨을 일부러 줄이신 것 같은데. 테스팅 테스팅 하나 둘 하나 둘 하나 둘 테스팅 하나 둘 하나 둘 하나 둘 하나 둘 하나 둘 이 스피커 밑 밑에 잡아.
테스팅 하나 둘 마이크를 테스트 중입니다. 테스팅 하나 둘 마이크.
Hello? Oh, all right. This is on. Hey, everyone. Let's go ahead and get our program started. Welcome to EGRAPHS 2025. Thank you all for being here. We have a very exciting program that I want to get to without too much further delay. We were slated for everyone to be here for in-person presentations, but unfortunately, due to some last-minute travel circumstances, we have two pre-recorded presentations, one of which will be this first presentation. So I really want to encourage to sort of make up for these folks who really did want to be here, to engage with these authors on the Discord or over email, or however you see fit to follow up with these folks, because I know that they did put a lot of time and effort into their presentation. So let's make sure to try to engage with them. Yeah, and with that, let's go ahead and get started with the program. Thanks.
Hi everyone, my name is Julian, and today I'll be presenting our work on using EGRAPHS for Boolean FHE circuit synthesis. To give a brief outline of the talk, I'll first introduce what fully homomorphic encryption, or FHE, is, and then discuss what FHE circuits are and how they're currently optimized. I'll then discuss our efforts to apply quality saturation towards this problem, and how that led us to our current solution, which we call cut tracing, using EGRAPHS. And then I'll present finally a preliminary evaluation of this method. Fully homomorphic encryption is a privacy-preserving technology that allows computation over encrypted data. Typically, the operations of addition and multiplication are supported. So I can take two messages, which we would call the plaintext, and encrypt them, and then on these ciphertexts, I can add or multiply them together to get what would be the result of adding or multiplying the plaintext values. In this talk, we're particularly interested in the case of those plaintext values being booleans, which we call a Boolean plaintext space. In this setting, additions and multiplications are equivalent to XOR and AND gates respectively, and so we'll use them interchangeably going forward. This case is of special interest because a Boolean plaintext representation is needed to homomorphically evaluate any algorithm that requires a bitwise number representation, such as a CRC32. In addition, using a Boolean plaintext space admits the use of Boolean circuit optimization techniques, which we will discuss further. However, the primary bottleneck of most FHE schemes is the overhead of these homomorphic operations, so for this reason, we're interested in how to optimize these computations and reduce the overhead. First, though, I will discuss how FHE computation is represented. We say a Boolean FHE circuit is a DAG of XOR and AND gates that compute homomorphically over ciphertexts. This is also called an XOR AND graph, and an example for a full adder circuit is pictured at the right. Our goal is to minimize the time to evaluate the homomorphic computation in this graph. The cost of doing so is primarily dictated by two factors: the multiplicative complexity and the multiplicative depth. Multiplicative complexity, which we abbreviate MC, is the total number of ANDs in the circuit and scales the runtime linearly. Meanwhile, multiplicative depth, or MD, is the maximum number of ANDs in sequence, or the depth of ANDs in the circuit, and causes a quadratic increase in runtime, mainly due to the fact that ANDs in sequence increase so-called noise in a ciphertext, and the ciphertext noise has to be globally increased to ensure that the decryption is still correct. And in turn, that has the effect of making every operation more expensive. Finally, XORs contribute a comparatively insignificant cost, and so are usually ignored for the purposes of optimization. Prior work on Boolean FHE circuit optimization has focused on peephole XAG optimization using so-called cuts, which are subgraphs in a logic network. Formally, a cut C is a set of leaves L and a root V such that every path from V to a primary input passes through at least one leaf, and each leaf is contained in at least one such path. If C has at most k leaves, we say that C is k feasible. So for example, on the left, a 2 feasible cut is highlighted in the graph. To optimize an XAG, first a set of candidate cuts in the graph are identified recursively using an algorithm called cut enumeration, and then for each candidate, some cost-specific algorithm is used to generate or resynthesize an optimized replacement cut. Finally, the replacements are applied greedily, such that only the replacement cut which has the best gain on the current circuit is used. For MC and MD specifically, two main algorithms have been introduced using this method: ESOP balancing and cut rewriting. ESOP balancing expresses cut candidates in an exclusive sum of products form, effectively resynthesizing the cut for a lower MD. And cut rewriting performs a lookup of cut candidates in a database of known MC optimal 6-input XAGs, which are indexed by the truth table of the cut. So if the XAG improves the MC, then it's replaced in the circuit. However, so far the problem of jointly optimizing those two metrics for FHE has not been considered. And so in this work, we seek to address that problem, attempting to optimize for the overall FHE runtime. As a starting point, we consider simply applying both of these two algorithms to minimize both metrics. And I'll show an example to demonstrate why this approach has its limitations, mainly that the algorithms don't really compose well and are prone to get stuck in local minima. The diagram shows the design space of a particular FHE benchmark, a sorting circuit. The y-axis is the multiplicative depth, and the x-axis is the multiplicative complexity. And the black dot shows the unoptimized starting point for this circuit. We start by applying ESOP balancing until convergence, that is, no further optimizations can be made to reduce the MD, which is shown in blue. We see that this also comes at the cost of increasing the MC slightly. Next, we apply MC reduction, and we notice similar behavior. We've improved on MC again, but then stepped back on MD. And actually, at this point, we're stuck on applying any optimizations. We can't apply either optimization to progress anywhere else without making both stats worse. Now, if we instead apply the MC reduction first, we also get to a completely different design. This one actually ends up being the best out of the three in terms of actual FHE evaluation time. But we're stuck even earlier. We cannot progress here with any optimizations. We can kind of see that the order in which these optimizations are applied heavily impacts the exploration of the design space. In other words, there's some sort of phase-up ordering problem here. So in light of these experiments, we consider equality saturation as a means to optimize FHE circuits. We store the XAG in an EGRAPH, like the graph at the right shows. So the two nodes at the root represent the two ways the expression x and y, x or z can be written by factoring it. And then we saturate the EGRAPH using standard Boolean XAG rewriting rules over XOR and, like distributivity, consensus, redundancy, etc. To extract from the EGRAPH, we use a scheme that's intended to represent HE runtime based on the insight that depth scales the cost quicker than complexity because it's quadratic. We select the best MD terms with a heuristic estimation for MC used to break ties. We used heuristics as we observed the EGRAPHs were too large for exact methods like ILP to be viable, but I'll come back to that soon. The result actually is that equality saturation is most often worse than the greedy ESOP and cut rewriting methods that I just showed. I'll give a small example once again to illustrate the problem. On the left, we have the same full ladder XAG that was pictured earlier. It has an MC of 2, so there are 2 AND gates. Since this is a small circuit, we know it's MC optimal implementation, which happens to be 1 AND gate, and that circuit is pictured at the right. So we'll try to use equality saturation to optimize the left circuit and find, hopefully, the optimal solution. After just 2 iterations of saturation in egg, the size of the EGRAPH has already grown considerably. And despite that, we still observe an extracted MC of only 2. It's worth noting here that we're actually using ILP because the circuit is small enough. So in other words, the MC of 2 is the best implementation present in this EGRAPH. It takes until 5 iterations until we get the optimal MC of 1 from the EGRAPH. At this point, the EGRAPH has exploded to contain 99 E classes and 394 E nodes. And as you may be able to guess, most of these nodes are in some sense unnecessary. The majority of them are doing some kind of restructuring, like applying associativity or commutativity, but not actually improving the best circuit in the EGRAPH. On the other hand, consider the process taken by cut rewriting, one of the algorithms to improve MC to optimize this circuit. The circuit is small enough that it appears in the database of 6 input functions, so in just one step, cut rewriting can find the optimal solution. A typical FHE circuit has thousands of nodes, and at that level, this gap in efficiency becomes a much larger problem and causes equality saturation to generally scale poorly compared to the traditional techniques. So, to summarize our observations on real benchmarks, equality saturation can explore a wider breadth of designs, but generally achieves a poor depth, so it's harder to find a solution requiring a long series of rewrites. And in addition, the amount of extra nodes generated by equality saturation means that extraction methods that accurately reflect the cost of shared terms, which we would want to reduce the multiplicative complexity, actually can't run. So we're forced to use heuristic methods, which degrades the results we get for MC. One strategy we can use to help is to use coarser rewrite rules that instead of manipulating individual expressions like with distributivity, we can replace larger chunks of the circuit at a time. For example, the rule is synthesized by a prior work on rewriting FHE circuits to reduce multiplicative depth. That strategy helps the first point, but we still have the problem of there's too many nodes in the E-graph, just based on the fact that equality saturation more or less applies rules blindly. So based on these observations, we ask the question, can we saturate the E-graph with fewer, in some sense, higher quality candidates? And that brings us to cut tracing. We observe that the classical optimization algorithms like ESOP balancing and cut rewriting already work on the principle of peephole optimization through rewriting parts of the graph, only that the rewrites are dynamic in some sense, so we can't just directly put them into equality saturation. But we can record the equivalence between a cut candidate and its replaced root in the E-graph. The diagram at the right sort of shows this process. An algorithm may identify the red cut as a replacement for the blue, while in the E-graph we would just simply record this information instead of destroying the blue, and we would just put the roots of the two cuts in the same E-class. So in cut tracing, we simply record all or some of the candidates that are generated by an algorithm like ESOP balancing or cut rewriting, even those that aren't the best candidate locally. And then at the final step, we can leverage standard eGraph extraction to extract the optimal term. Of course, the caveat here is that there is no E-matching. All we're doing here is simply remembering every design choice generated by the algorithm. So in some sense, we're still constrained to the design path taken by the original algorithm. We can't exactly deviate by applying something else to the eGraph. Surprisingly though, in spite of this, tracing can still identify some sizable optimizations. To further elucidate how cut tracing is used, we present our flow. We apply the same combination of cut rewriting and ESOP balancing, each until convergence, and this flow produces our baseline. Meanwhile, we modify these algorithms to also record every replacement candidate identified in the eGraph. Then at the final step, we extract this candidate using some FHE evaluation-oriented algorithm. In fact, actually for this, we're able to use ILP again. Since we have so much fewer candidates in the eGraph, we can even add constraints to the ILP formulation, which normally would just take the optimal MC term. We can also tell it to filter MD so that we end up with a solution that's optimal in both. In other words, we're able to extract the optimal MD and MC term from the eGraph and then get the optimal circuit runtime from the eGraph. We evaluate our flow against the baseline circuit in two scenarios. First, we apply MC reduction with cut rewriting, then MD reduction with ESOP balancing, and the second, we try the other order. The table shows the speed up in the homomorphic evaluation runtime of the cut tracing over the baseline on a suite of benchmarks. And the second ordering is in parentheses, so MD, then MC is in parentheses. We can see that in the best cases for the first order, which happens to be the better overall for the baseline, cut tracing can yield up to a 40% speed up. Overall, we get around a 10% speed up. We can also see that even though there is often an improvement, the results are still quite heavily dependent on the order, which is to be expected from the fact that we're not really deviating from the path chosen by the algorithm. Also, in some cases, cut tracing yields a worse result. With optimal extraction, this shouldn't be the case because it should simply find the same solution used by the baseline. But the issue that we suspect is that the extraction is still not optimal because of cycles that can be introduced, and this is a typical problem for ILP. We notice that what happens usually is that the algorithm introduces some replacement cut, which is a subgraph of the original, and so then there's a cycle that appears in the eGraph. This is an active area of improvement for the tool, and we're investigating how we can reduce cycles in the eGraph. We also highlight the B-sort circuit, which we showed the design space of earlier. With cut tracing, we're able to find a design that's better than both of the paths taken. It makes a very small compromise in the MC as compared to the MC first path, which was the old best solution, while having the same MD of the other path. So overall better than both, more or less. Finally, we also test cut tracing versus normal equality saturation. For this experiment, we used the synthesized FHE circuit rewrite rules, which I mentioned prior, with the greedy extraction method we also highlighted earlier. The full benchmark suite is not shown here, but we can see that not only does cut tracing provide a 30% overall improvement compared to equality saturation, with, in the best case, a 2x improvement, but even the baseline of simply combining ESOP balancing and cut rewriting also provides a 20% improvement. So equality saturation ends up being worse than just the baseline. And in general, that mainly comes from the fact that we are forced to use a suboptimal extraction instead of ILP here, which won't actually accurately estimate MC. And so then even the baseline finds an improvement because of this. So to conclude, we wanted to optimize Boolean FHE circuits for their overall runtime, which is some combination of MD and MC, instead of just one at a time. So for this, we proposed cut tracing, which is a method that uses EGRAPHS to expand the design space explored by traditional optimization algorithms. In this sense, it's a small step towards combining classical optimization techniques with equality saturation. We saw that it improves sensitivity to the ordering of the passes, though it's limited due to not using the eGraph in the optimization process itself. We are interested to investigate how to integrate e-matching and incorporate the eGraph better into this flow so we can reap more of the traditional advantages of equality saturation. Of course, we would also like to maintain a small enough eGraph so that we can keep using this optimal extraction, which we saw was important for the application. And as mentioned, we also faced issues with cycles in the extraction, which is an active area of improvement. Our code and preprint is available at the link in the QR code. Thank you for your attention, and I will take any questions.
Okay. Yeah, and again, I just want to reiterate, please, hop into the Discord and feel free to ask the authors. I believe some of them may be online at this very moment. Yeah, please go ahead and do that. And then let's go ahead and get the next speaker to go ahead and step up. Oh, okay, fantastic. The speaker is actually live on Discord, so if there are questions, let's go ahead and take those, and we can get answers in real time.
Hey, can you hear me? My audio is working.
Okay, I'll go ahead and start us off with a question. Thanks for the really great talk. I'm noticing a similarity between the method here of sort of acknowledging that rewrites are not the right methodology to accomplish some transformation, and sort of instead you want to do something outside the eGraph and then sort of record the results back in the eGraph. This reminds me of the trick that many folks have done for substitution and beta reduction when like optimizing a lambda calculus. It's really slow to do that explicitly, but you can sort of just extract a term and then do whatever you wanted to do with it and then put the result back in. And the nice thing about, at least in that setting, is you could sort of just do that, ad nauseum, right? There's no limit to doing that. So is that something you considered for your approach? Like, at least from what I understood of your flow, it sounded like you were sort of limited in the number of steps you could take, but could you just keep pulling eGraphs out and then doing the cut algorithm and then putting them back in over and over again? Would that potentially be helpful?
Yeah, I think there definitely is some similarity in what you're proposing. I think let's see. I think maybe the difference is that with something like beta reduction is with like the example you gave that I understand it, is that you're sort of applying like that the rewrite you're doing is moving in the direction you want in the eGraph, and so you would sort of like to apply that in a way that doesn't add more e-classes in the eGraph. And so what we're doing, I think, morally achieves the same thing, although it exists completely outside of the eGraph. So you do, with our method, like you do run into a wall where like you may not get any better circuit, because you would like once you run this enough times, you may not get any more improvements as well. Like you could still hit like some kind of local minimum because you're still in that same design path of the original. But I believe, yeah, it is a very similar technique. Yeah. Thanks for the question.
Yeah, I'll follow up on offline with that. Do we have any further questions for the speaker? Okay, we have maybe time for one more.
Hi, thanks for the great talk. Can you explain what is like the fundamental difference between the cut tracing and just a rewrite? Like you were recording equivalences in the eGraph. Like why could it not just be like a big rewrite? Like what is fundamentally different
Yeah.
between doing that and rewriting?
Yeah, I think the two key differences are with these algorithms, you take like your right hand side of your rewrite rule is generated dynamically based on what the left hand side is, and you're also matching. It is matched structurally in the graph to begin with. Like the cut enumeration is also a structural enumeration, but in order to achieve the same thing, um, if you were to apply it to an eGraph, like with a rewrite rule, you would want something that matches over the truth table of like identified cut to get that right hand side and not just the structure. So like it would be it is fundamentally different than having like a static set of rewriting rules in like at the start of your program that you then saturate your egraph with. But it could be the same thing as like yes, having some rewrite rules that if you can dynamically generate the like if you have an e-matching procedure that can give you if you have an e-matching procedure that gives you like a left hand side or you have your left hand side and you can run some function that optimizes that and then place that in the egraph, then it would be the same thing as that. So it is sort of just that the rule is dynamic in some sense.
Okay, and with that, let's thank the speaker again and switch over to the next presentation.
Check. Okay. So, can I start? Okay. Okay. So, optimizations. Okay. So I'm Hiramishi from GIJ Inc. So I'm so honored to be here. So, okay. So here's today's topic. So first, we skim through overview of our product GIJ modeling and the problem of constraint detection, and see some performance measurements, and then introduce some heuristics. Heuristic lessons run from our implementation. Okay, so let's start with overview. GIJ modeling is a mathematical optimization modeler provided as a Python EDSL implemented in Rust. And for those who are not familiar with mathematical optimization, modeler is a tool to describe the and encode optimization problems as some sort of mathematical versions. And the solver solves them exactly or approximately encoded problems exactly or approximately. And this is used in production or company on daily basis. And here is the example program that encodes traveling salesman problem and quadratic formulation. So you can see it is it seems some kind very resembles the mathematical model presented here. Okay, so enough for advertisement. So let's dive into the motivation that related to eGraphs. So constraint detection problem. So the point is that there are specific types of constraints which can be exploited to solve problems efficiently. So there are so-called one-hot constraint or unit simplex or special ordered set of type 1 or 2, etc., etc. And the previous example of TSP indeed involved so-called two-way one-hot constraint. So, so note the interchanged subscript here. So these two constraints jointly constitute a two-way one-hot constraint. And solvers provide dedicated APIs for specifying such constraint explicitly to gain the solution time. But the problem is that if one is expertise in mathematical optimization, they can find they can spot such good constraints by hand. But many practitioners need not be it is not necessarily be aware that such constraints they are writing such good ones. So here's the so-called constraint detection problem. We coined that term. All right, so modeler should detect such constraints from even unaware user input. So to call dedicated API automatically in place of users. So here are two challenges in constraint detection problems we solved here. So one is to avoid combinatorial explosion. So detection time must not depend on input size. And here, n is not the number of equation, but actual input size. So array, or so in the TSP example, n is the number of CT, or so yes. So it must depend only on number of equation, but not actual real-world data size. So if we detect the above two-way one-hot naively, one must match against n times in the formula, and so if there is one matching this one, then try everything else to find this pattern. So this will lead to the combinatorial explosion when done naively. And the second challenge is we have to take algebraic congruences into account. So there can be several ways of expressing the same constraint. So for example, so these three formulae are all equivalent, and so we must detect each terms as equally equally. So how GLG modeling solves these problems? So the point for the first point, the combinatorial explosion, GLG modeling separates symbolic representation from input data. So instead of expanding summations or for-all constraints, it stores them as is symbolically. Well, it might sound rather trivial to programming language people, but in the industry of mathematical optimization, vast majority of modelers treats formula and input data in mixture, and the task of constraint detection problem almost infeasible. So we are just buying into using ASTs. So and then two-way one-hot constraints from the previous slide is just two formulae. So we can just find two formula is Okay, so the second point is algebraic congruence, and as you might guess, we employ EGG to compute congruence closure here. So, and one possible alternative is to define some normal form and compute them and compare them. But we didn't take this route because the term language is somewhat complex. Okay, so let's skim through our complexity of the term language. So the term language of GLG modeling consists of two layers. So one is expression language. So it contains arithmetic operations and reduction operators or aggregations. So here, not this. Yeah. So this particularly involves bound variables and arithmetic and etc. etc. Okay. So and we are working on version 2 with arbitrary lambda abstraction. And constraint and it contains constraint terms. So comparison of the two expressions to be used as a constraint of mathematical optimization problems. So we don't think any feasible complete normal form can be defined for it. So we decided to use EGRAPHS. Okay. So it's the overview. So first, see the performance measurements. So okay. So as an example, we are interested here in so-called special ordered set of type 1. So briefly, this demands a list of non-negative variables. So exactly at most one of non-negative variables to be non-zero. Okay. And the important point is that if the data is mixed with expressions directly, this term will become n many formulae. So we must use symbolic representation to just pattern match against 2 instead of m times n plus 1. Yeah. And the particular problem we are trying to formulate is the two-plant placing problem. So briefly, we are to place plant in each east and west region to minimize some cost. So detail it doesn't matter, but the point is here 2 SOS1 constraints, and these are encoded in this style of using big M-like notation to encode it as a equation. Okay. So we formulated this in GIJ modeling 1.12.3 and using PySkipOps solver as the solver, and compares without detection version and with detection version in terms of runtime. Okay. So the first, let's see the runtime in without detection. So if we don't exploit the information in SOS1, the runtime seems exponentially grow. It shows exponential growth. On the other hand, if we detect SOS1 automatically, it is very constant or linear, it seems. So asymptotic improvements can be achieved. So even if the input size is only 60 or so, this difference is evident. So in practice, our constraint detection problem, solving constraint detection problem, really buys something to us. So with timer, it usually takes approximately 1 second for constraint detection. So, and in practice, solving problems takes much more time. So this overhead is almost negligible in your adaptation. And we haven't measured the saturation rate yet because completeness of detection with respect to algebraic growth is not so important in practice, because we can already cover some variation and equations that can arise naturally, I think. So we think it works well. So okay, so it gives us indeed great speed ups in solving problems. So let's go to the case study part of constraint detection, implementing constraint detection in terms of EGRAPHS. Okay, so we will talk about architecture of our constraint detection with EGG in GIJ modeling, and heuristic for writing rewrites learned through the course of implementation. So here are some rules. And finally, we introduce some utility Rust library built on top of EGG library. Okay, so our constraint detection proceeds as follows. So it first converts each constraint into a separate EGRAPH. So separation is not essential, but for simplicity reason. So it allows identifying original constraint without IDs, with issuing IDs. So we can just match against each EGRAPHs and avoid bound variable collision here. And saturate with rewrites and analysis. And the analysis part consists of two parts, typing and constant folding. Why we need typing here will be covered soon. Okay. And then apply patterns to each EGRAPH for detection. Okay. And currently we are manually checking conditionals for composite detection, such as SOS1 for general variables. Okay. And here is some excerpted rewrite rules. So it consists of rules for constraint terms. So equality or inequality rules. Row, and some algebraic rows involving reduction operators, and that lattice rows, Boolean operations, and for Boolean and orthoric applications. And we will cover why we come up with these rules from now on. So first heuristic to choose these rules is bidirectionalized rules. So there are some bidirectional rules in the previous slides, and this is because we perform pattern match externally after the saturation. So suppose we are to detect term, so in the left associated form of ternary sum, then, and further, suppose saturated E graph contains right associated variant, then if the associative rho is only unidirectional, the saturated graph does not include the form of these refs associated ones. Hence, the matching against this pattern will fail. So listen, so always bidirectionalize rules for completeness when, at least when you perform matching after the saturation. Okay. So the heuristic 2, it's a use type information for soundness. Okay. So there are some rules guarded by side conditions on types, such as A to A plus 0 if A is real or float. And this seems the opposite direction of A plus 0 to A. So why not just bidirectionalize it according to the previous rule? Well, this is because the opposite rule can reduce type information. So if A plus 0 is well typed, then we can infer that, well, by our definition of language, A must be float number, but not vice versa. So if we have a conditional rules instead, there is to ill-typed writing, such as true to true plus 0, which doesn't make sense at all. And such a write might seem harmless at the first glance, but in our experience, indeed such rules once made all floating numbers equal. For some reason, we couldn't make out the exact reason, but it does happen. Yeah, and adding such type side conditions, such behavior disappeared. So this is why the reason why we are currently having typing in our analysis phase. So listen. So when treat multi-typed language, use type information to ensure soundness. Yeah, this is very crucial. And the heuristic 3, prefer reductive rules of analysis. So there are some rules that follows from other rules on constant foldings. So for example, A plus minus A to 0 can be derived from other rules and constant folding as follows. It might seem adding overhead to the saturation, but in our experience, adding reductive rules like this dramatically improves saturation time. And we didn't have time, so we couldn't add the benchmark result here. But for some terms, in our experience, it took approximately 5 seconds to reach the fixed point and without the rule, but only less than 1 second after adding such reduction rules. So lesson, do not rely on constant foldings. Adding reductive rules can improve saturation time. Okay. And the saturation here means saturation or timer, but for small terms, it indeed reached to saturation. Okay. And here, and these are the heuristics, and okay, only 3 minutes left, so we will skim through egg recursive in brief. So we during the course of development, we also developed the egg recursive built on top of egg. So this allows us to use egg without S expressions. So some egg expression-based API has some downsides. We think so. It relying on from string and display, or its expressions are parsed at runtime, not compile time. So even if the given expression has syntax error, users cannot notice. And complex expressions are just hard to parse by humans. And the hard to comprehend the meaning of positional argument expressions, and egg recursive aims to solve these pains. And for example, this is the typical example of egg rewrite rules, and this becomes this. So everything was coded in string, but now it is written as genuine last program. So here we use times and plus operators here. And I bet you're not aware this closing parenthesis is redundant or extra, and it will lead to runtime error, but we are not aware. So if we use S expression-based interface, we are not aware of this extra closing parenthesis. So, but if there is such thing, Rust compiler will warn us. Okay, we see. It seems that we are running out of time. So we can derive such. Okay. So and we can just large arguments can be guarded with view types that provides named arguments. Okay, and we can derive such definitions and smart constructors with macros. Okay. Okay, so future work and conclusion. So there are much future space for future work. So we are considering using egg log instead of egg. So it should remove the current manual conditionals and the bindings. So detection of SOS1 on general variables involves the first detect the SOS1 on binaries and then general non-negatives. So such conditionals can be expressed naturally in egg log, we think. And apply threaded graphs to treat bound variables properly. So I will attend the talk tomorrow. Yeah. Okay. And also use EGRAPHS to solve typing constraints on a tensor shape in our version 2 of JJ modeling. So we have dedicated type system in upcoming version 2. So we can use EGRAPHS only also in typing, we think. And we are planning to remove typing analysis phase in favor of proper type system. Yeah. And consider combining EGRAPHS with partial normalization and constraint detection. So store constraint only form of E1 is less than or equal to 0 and normalize it. So this is a suggestion from reviewer A. Thanks. Okay, here are conclusions. JJ modeling is, to our knowledge, the first versatile mathematical optimization modeler supporting constraint detection mechanism. So it detects specific constraints that and tells solvers to exploit such information. This will improve the solution time dramatically, and EGRAPHS play a crucial role in such mechanism in JJ modeling. And we skim through some lessons, and we also introduce some egg recursive crate. Okay, and part of this work is performed for Council of Science in Japan. Okay, here are references, and thank you.
Thanks so much for that great talk. I think we have time for one quick question while we change over speakers. So if the next speaker could just go ahead and get set up. Do we have any questions from the audience? I've got a quick question. In terms, one thing that you didn't mention is the role of extraction. I know that that's a problematic area for a lot of these eGraph applications. Did a sort of straightforward approach work for you, or did you have to do something more complex?
Yeah, we didn't. We just matched against eGraph, but not extraction, because we want to preserve the user input, the form of user input. Yeah, but indeed, there must be space for exploration to optimize the expression of mathematical optimization. So that must be interesting point. Yeah, thank you for the suggestion.
Okay, sounds good. Well, let's thank the speaker again, and
thanks.
Let's get set up.
can you hear me? Or maybe it should be. Hello. Yeah, but is it high enough? Hi, I'm Oren, and I'm gonna speak to you about optimizing molecular dynamic simulations together with my advisor and collaborators. So first of all, what is molecular dynamics? Essentially, it's simulating molecular interactions accurately. And we can see here a simple simulation of some water molecules. You can see all the molecules vibrating and interacting with each other. And this whole simulation simulates about 0.1 nanoseconds of interaction. So the general recipe for molecular dynamic simulations is a very simplified recipe, of course. It's like first you start with some initial conditions. You start with n atoms at positions r and some initial velocities. And then you repeat for n steps. And then simply you compute forces between and inside molecules and update the positions and the velocities or momentum via Newton's laws. So you can see this is a relatively simple update loop. Obviously, the real programs are a bit more involved. So why should we care about molecular dynamics? Well, there's a broad community of scientists that write and run code, and we're interested in code and optimizing code. For example, our collaborators, Yotam and Barak, which are computational chemists. And second of all, simulating milliseconds can take months or years of simulation time. And this is a very slow process, and in some cases it even prevents simulating some process at all. Like you cannot even run it, and you will never terminate in time. So some of the pain points is that many computational scientists roll their own code. There are a lot of missed optimizations, but most importantly, it's really, really slow, as we just mentioned. So part of the reasons that it's very slow is that, let's go back to our water simulation. Then there are forces between molecules, and there are forces inside molecules. For example, here it's between the hydrogen and oxygen atoms. And forces between molecules, you have to compute them between every pair of molecule. And it's obviously scaling quadratically. And you want to be accurate, so you work in a very small time steps. So you can see how much happens during this 0.1 nanosecond simulation. So this is a general reason why it's so slow to compute accurately. So some existing recipes to make this molecular dynamic simulation faster are some vectorization and parallelization, evaluating expressions more efficiently, and there are some also generic algorithmic improvements. We will not touch on this point, but we will focus mainly on these. As you can maybe guess, the evaluating expression more efficiently relates to EGRAPH, and also the third point, which we will discuss in a bit. So our goal is to make molecular dynamic simulation faster, and we want to do it by two different approaches. First, the classic approach of optimization by axiomatic equivalence through equality saturation, and with a twist for our domain. And the second approach is optimization by break-in equivalence, even if temporarily. And we do this in order to rediscover known and new algorithmic techniques in the field of computational chemistry. So this is also done with EGRAPHS as a building block, which we'll see in a bit. But we will start with this part of the classic use case. So what does this have to do with EGRAPHS? Well, you might have guessed it, but first we will follow the generic recipe of using egglog, some domain knowledge, and then hopefully we get some profit in that. So super optimization of molecular dynamics programs. We will go through some examples as we discovered in developing the optimization phase, and some practical lessons we learned. So a lot of molecular dynamics programs would benefit from algebraic, vectorized, and domain-specific rewrite rules. From a short survey we did, there are a lot of misoptimizations. And this is a bit more elaborate version of the code we saw on the first slide. You don't really have to read it. We'll zoom in a bit. We will focus on these two lines. So the first line is computing the the norm, the distance between each pair of particles, the Euclidean norm. And the second line, it computes some kind of force between them. And we can see it uses the distance matrix computed earlier. But actually, there is something missing here, some missed optimization here. Maybe if you notice, there is a hidden square root in the calculation of the norm, and we only take even powers of this matrix. So actually, we don't really have to perform this expensive operation in order to compute the final force. So this brings us to like 2 example rewrite rules we came up with. That norm is like essentially the same as the square root of the sum of coordinates squared, and square root is essentially raised into the power of half. And this is just an example of one of many optimizations that are this real-world molecular dynamics simulation code in Python provided by our collaborators, and this is just one example. So, is it enough? Well, not quite. There are some practical lessons we encountered during developing these sort of optimization rewrite rules. The first one is, how can we cancel this expression, the square root of x to the 4th? Well, essentially, we need to know the fact that 4 is 2 times 2, right? Because we need to divide 4 by 2. So how to do that? Well, we can have a rewrite rule that says that if q divides p, then p is the same as p divided by q times q. So this seems to solve it, but there is one challenge that we ran into, which is has been called online mostly as demand rules. What are demand rules? In order for this rewrite rule to fire, we need both p and q to be present in the EGRAPH. Well, if you want to fire this rule, then obviously you need to decompose the number before you apply this rule. But how can you actually know if you need to decompose something? Well, you can't. So our current non-ideal solution is factor in all constants in the program, which is not a complete solution, and it's rather slow, but this is our current workaround for this problem, which is that you need to have all conditions satisfied statically. You cannot explore some path. So, okay, another lesson is that obviously we want to differentiate between these 2 expressions. Matrix multiplication is associative, and one of them is probably more expensive than the other. For example, the top one has 500 multiplications, the bottom one has 1,000. So we need to assign different costs to them. And up until recently, eglog did not support dynamic cost per operation, only constant cost per operation type. As was mentioned in yesterday's tutorial, it does exist in the eglog experimental repo. So, but nevertheless, before this was developed, we extended eglog with custom cost functions and custom extractors in Python that we can write ourselves. So these are 2 exemplary lessons we had. So let's go back to our second way of optimizing, because we may have run this equality saturation on the molecular dynamics programs, but we may be stuck at a local minimum of performance, and maybe we can do better. And this was explored previously by computational chemists, and so let's go into it. So multiple time stepping, what is it? Let's go back once again to our water simulation, and we saw there are 2 forces acting between and inside the molecules. There is the librational force, which acts between molecules. It has very slow dynamics, which means it's changing relatively slowly in time. It's still very fast, of course. And there's the vibrational force between the hydrogen and oxygen atoms that has very fast dynamics. The atoms vibrate much faster than they interact with far molecules. So what does it mean? Well, it means that we can evaluate the slow-acting force less frequently. How does it look practically in code? Let's assume we have some loop that updates the velocity or momentum with both forces. And then we can actually hoist it out of the loop, the update of the velocity by the slow force, but also multiply by the appropriate time scale. This is, of course, a very non-equivalent step, but in some cases, it's good enough. Why is it good enough? Well, basically because chemists say so, but actually, we can mathematically derive multiple time stepping and bound the error it introduces. So now this brings us to talk about concepts of equivalence, because this was a very non-equivalent transformation. So we present this sort of pyramid of like different equivalence concept going down in like decrease in accuracy. So first of all, we have the axiomatic type of equivalence, which is what we all know. It's a sequence of mathematically equivalent rewrite rules. All programs produced by it are the same, at least semantically. And then we also have some kind of equivalence, which is called distributional. What does it mean? It means that the final statistical distribution of the particles matches the unchanged program. Why is it important? Because these are actually the properties that are computed by these kind of scientific simulations, at least in this domain. And finally, we have functional equivalence, which means that some domain properties, for example, energy is preserved, but maybe other things are not preserved. So this is the broadest class of programs, and also it's very fast to compute, as opposed to distributional equivalence, which is very slow because you actually need to test the equivalence over multiple runs to check if the distribution is the same. It means that each particle can end up in a different location, but combined they make up the same distribution. So how to actually achieve multiple time stepping? And we will see it by programmatic transformation and not by math derivation. And we will combine several types of mutations, both equivalent mutations and stochastic mutations. So let's go into the example. So let's go back to the code we saw on the first slide. I remind you that we started with n atoms. We compute forces between and inside molecules, and we update the positions and velocities. So notice that now we have two types of forces. We have the fast-acting force and the slow-acting force, as opposed to the first example. So we wanted to compute the slow force less frequently. So we cannot really do it now unless we only do it once in the beginning. So first of all, we need to split this loop into two. So we can perform this equivalent step provided k divides n steps, and split the loop, which is an equivalent transformation. Now we still cannot actually break it out of the loop because they're computed in the same expression, in the same line. So we would want to decompose this line into two, which is another equivalent mutation. So we did this expression decomposition, and now we can proceed to compute it less frequently. So now we can actually hoist all the expressions involving the slow force out of the inner loop. So we do that, which is a very non-equivalent step, and it also doesn't preserve any sort of equivalence yet. We did the loop hoisting. So what's missing is the time scale is not right. We hoist it out of the loop, but we still need to multiply it by k. So we will do that, which is another very non-equivalent step, but together combined with everything else, for some types of systems, some kinds of forces, it preserves functional equivalence. So this is another non-equivalent step, the expression mutation. So overall, now we showed multiple time stepping in using some programmatic transformations. So what happened? We applied some local equivalence breaking mutations, which broke all kinds of equivalence temporarily, but also purposely. But when they're combined, we can get equivalence back, at least the functional one. And a key takeaway is that some equivalent transformations can unlock new possible mutations. As you saw, we had to decompose the loop and the expressions in order for us to apply the non-equivalent multiple time stepping mutations. So how do we actually do it? Well, how do we apply non-equivalent mutations? Randomly, we pick some line or expression and we mutate it. And how do we apply equivalent transformations? Also randomly, we still pick a line or an expression, but we use an EGRAPH on it, which we will talk about in a bit. We use the EGRAPH as a component in this kind of mutation. So we call this an EGRAPH guided mutation. You can see the EGRAPH to the right, which represents this equivalence that half times fs plus fslow is equal to is equivalent to half times fs plus half times fslow, obviously by distributivity. But maybe the top expression is cheaper because it only performs a single multiplication as opposed to the bottom one. But we may still want the bottom one. So the EGRAPHs contain many more representations other than the optimal one, and we explore this space with custom and dynamic cost functions we develop. Custom means that it can depend on child nodes or functions such as shape, and dynamic means that it can depend on the location in the graph. For example, we may choose randomly that we want to perform an expression decomposition, and we only want to decompose the outermost operator in some expression. So we put everything into an EGRAPH, we give it the proper cost function, we saturate it, and then hopefully we can decompose the expression, which will help us proceed in our search space. So this brings us to our overall workflow, which is a mutate verify loop. The mutate phase contains these two types of mutation, which is the EGRAPH guided mutation and the stochastic random mutation. Obviously, the EGRAPH guided mutation is equivalence preserving, and the stochastic random mutation is probably not equivalence preserving. So that's why we feed the result of this stochastic mutation into a verify phase, which can perform functional tests and axiomatic equivalence tests. We don't need to do it in the case of equivalent mutations, and then we can feed back the results of the verify into the mutate phase. Notice that we can explore several steps deep without preserving equivalence, but eventually we will want to reach some equivalent state in some sense. Notice that we don't have distributional equivalence because it's very expensive to test. So finally, after we explore the search space for a bit, we want to optimize all programs using equality saturation, but only for equivalent programs, because in the end we want programs to run as fast as possible. So this relates to the first part of the talk. So currently we implemented some basic versions of these components, and we plan to both extend them and make them more generic to operate on real-world code using eglog and eglog Python bindings. So let's conclude what we talked about. We wanted to make molecular dynamic simulations faster, and we do it by two ways. First is the classic use case of equality saturation, which is optimization through axiomatic equivalence, and we also explore optimization by break-in equivalence, which may help us discover existing techniques like multiple time stepping and hopefully maybe new techniques in the future. Thank you very much for listening.
Thanks for the great talk. We have time for a few questions before we head to the first break.
Hi, thanks for the great talk. That was super awesome. I'm really curious if you've thought about how you can maybe expose some sort of knob to the domain experts where they can say how equivalent they want something to be for their downstream applications. Maybe, you know, it's really important that the time step is not going to exceed like, you know, this amount or something like that. I'm just curious to hear if you have any thoughts on that.
Yeah, this is a very important concept. Obviously, all the equivalence types, which is non-axiomatic, we presented here are brought to us by the domain experts, which are the computational chemists. And we haven't really started to implement some sort of user-facing system to consider this, but this is something that we're very much interested in doing in the future.
So fantastic stuff. I really like the idea of breaking equivalence and saying that, you know what, actually this is okay because I know eventually this is going to be functionally correct. You mentioned, and maybe I misunderstood, that as part of that, you might break equivalence and then restore it later as part of a downstream set of transformations. that seems like it might interact in a complicated way with how frequently you verify. If you verify too frequently, you're always going to say, no, you can't jump that gap. And if you verify too infrequently, you could get too far away from anything that's correct. Have you thought about what that interplay looks like?
We haven't specifically explored what you're suggesting, but because this depth is configurable, then we can allow it to search into more non-equivalent depth. This is something that we need to consider.
Really interesting. Thank you for the talk. Yeah, the notion that you have like multiple notions of equivalence is really interesting, and I think that's a phenomenon I've sort of seen where you have like refining notions of equivalence. It kind of seems to me like you really had this pyramid where like the lower parts of the pyramid inherited from the top parts of the pyramid, and I think maybe this can be encoded sometimes by like really trying to make like these are like semantically or these are different things that like translate between each other being protected by function symbols. Like there's a whatever. I don't know if there was an eGraph that supported like multiple notions of equality intrinsically, would that be useful for your application? And like that, like the lower parts of the pyramid immediately inherit from the top parts of the pyramid, and were the lower parts really equivalence relations, or were they not equivalence relations?
Yeah, we thought about incorporating like these non-equivalent rewrite rules into the eGraph, but we haven't really gotten into it yet. We're still implementing the basic version of our tool, but this is a really important distinction that we can make in the future, that we can build everything using an eGraph. We haven't gotten into it yet.
Thank you.
Okay, and with that, let's wrap up our first session. Let's thank the speaker one more time. And with that, we'll head to the first break. We resume at 10:30. So yeah, feel free to find the speakers and ask those other questions there. All right, thanks folks for coming back to the next session. We have 3 more talks focused on applications. Yeah, Jenny, when you are ready, take it away.
Oh, thanks. Right. Hi. Hi everyone. Today I'm gonna talk about a toy project that we recently developed called EGRAPHS. It's an equality saturation dialect for non-destructive rewriting. It's basically combining MIR and EGRAPHS because both are cool. So here is the simple compilation flow that takes a source code and compile all the way to the executable binary. So here we can see the code is transformed into or lowered into different IRs, increasingly lower level of abstractions. So we might have a loop level or then instruction level. So X useful. So we can use that to rewrite our expressions. So apply this rewrites non-destructively. So user can define new rewrite rules for different patterns based on their application domains, and then they use E classes to analyze the properties of these expressions. So it's quite easy to support rewrites at a different level of abstractions. But the problem is most tools build on top X, and they are not tightly integrated in the compilers. So the developers often have to implement these conversions between AG and their frameworks. So for example, like from eGraph to their program representation, and in most time, it will require a lot of development efforts to do the translation, and most importantly, the equality information of the program is often lost during the conversion. So it's not possible to carry all the equality information across the abstractions in this compiler, transformations like function calls or function inlining analysis between different abstractions is quite challenging. Yeah. So CraneLift has done a great job. So it's a JIT compiler backend, most used for compiling WebAssembly and the Rust code. So it embedded like eGraph into their IR, also called as acyclic eGraphs. So they have optimizations like global value numbering and looping invariant code motions are handled by the eGraph optimizations. So there's no real conversion. So everything is done natively. But a limitation is that it only works in CraneLift. So it's not possible to extend at higher level of the abstractions earlier in the compilation. So for example, if I wanted to target a deep learning application, then I cannot really do some tensor level primitives. So the motivation is, how about we combine the best of both worlds? So can we actually implement a tightly integrates MIR framework that with eGraphs? So maintain the equality relation throughout different abstractions with different compiler passes. And ideally, we should be able to handle equality saturation at different level. So what is MIR? So MIR is one of the most popular framework in compilers. So has many different dialects at different level of abstractions. Here we have 3 set of different examples. So the first one is Lineage. It has high-level linear algebra operations like matrix multiplications. So it operates on the tensor level of values. And there are also lower level of abstractions like structured control flow 4. So that's basically represent a for loop. And we also have other operations like arithmetic operations for addition and multiplication, and also memory operations like load and store. Even further, we can lower this into specific targets. So it's like LVM floating point add or RISC-V floating point add. So the idea is like, or our vision is try to build equality saturation on top of MIR to give our extensible flexibility to explore across all these dialects. So the question is, how do we represent eGraph in MIR? Like the key idea is like we don't want to translate MIR code to AG and this is what have been done. So can we actually express eGraph in MIR in this case? Here is a simple example. On the left, so we have a function that takes one argument and return one result. So the right-hand side is basically the AST of the program. We have a times a constant of 2. So intuitively, this is the eGraph that we have. I guess everybody's bored with the figure on the right. So the interesting thing is, how do we express this as MIR code on the left? So so basically we introduce eClass op as an operation that takes a variable number of input and return a single output. So in this case, all the values are passed to an eClass operation and then return a result. So what we observe is each arithmetic or each non-eClass operation will take a set of operands in eClass and then return an eNode. And the eNode will be passed to eClass, right? So how do we express different eNodes in the same eClass? So one possible example in this case is a shift left by 1 is equivalent to a times 2. In this case, we will, so the black lines of code represents the new expression. So first we have the new constant that is 1, and we wrap them as eClass, so that's straightforward. And then the shift operation is equivalent to the multiplication. So what do? Is we introduce a new operator and we insert the value into the operand list of this eClass. So we will have, so basically, we just introduce a new representation. We have all the problem that egg has experienced before. Here we focused on the expression of this different eGraph representations in MIR. So one well-known thing is cycle. And in traditional MIR program, or in most sequential program, we cannot represent cycles because variables has to be used when it after it is declared. MIR has a structure called graph regions that allows programs to be, or graph to be represented in MIR. So in this case, we use graph regions to represent eGraphs. So it's more like standard SSA CFG regions. So this allows us to express regions in IR. Oh, sorry, cycles in IR. So how about union or rebuilding? So we consider that as a compiler transformation. So the insight is, can we actually reuse existing compiler optimizations to help our rebuilding process? So egg introduces has union, which is like efficient to maintain the congruency invariance. So here we have an example, like we have two, after we apply rewrite rule, we come up with different expression of eGraph. Now we want to merge them together. So if we find that A and B are equivalent, so then we can easily see that res0 and res1, which is function of A and B, are equivalent. But currently the graph on the left is not really an eGraph because these two eClass should be merged together. So what happens here is we can run this CSE pass to remove redundant terms and then keep only one eClass in the graph. Right. So the other thing is, how about rewrite rules? So traditionally in egg, we have rewrite rules declared as a pattern rewrite. And in MIR, we also have pattern-based pattern rewrites. So user can basically specify a pattern, input a pattern of the MIR operations, and they specify how this can be translated. So our implementation is based on PDL dialects, which is called pattern definition language. So it's basically the code might look quite complicated, but the key idea here is the user user can specify the patterns of MI operations, and they can also specify how the transformed MIR code look like. So this is equivalent to the rewrite rules. So what I can share here is a very simple example. So it's like if we have multiplication, that's x times y, and we can find an equivalent term that is y times x, is equivalent to y times x. The first thing that it does is the PDL rewriter will try to identify these operations using pattern-based rewrite, and then we will find the results by identify the E-class of this operation, and then we will basically find this E-class will contain multiple E nodes. So there are two more operations that implement PDL rewrite, but basically what it does is it will insert the newly created term and insert that into the E-class. So everything sounds very straightforward, but it's not. So if you actually apply PDL rewrites directly on to MIR programs, then we find something interesting. So ideally, with rewrite rules, we have different levels. You can add in different equivalent terms into the eGraph. That sounds really fancy. But what we find here is we might actually got a different isolated eGraph because they are targeting different abstractions. So that's not what we want because, for example, we have for loop, then we have eGraph for the for loop header or the structure, and we also have another eGraph for the loop body. But actually, there are correlations between the eGraph, the loop and its loop body. So this is something we haven't solved yet. We are currently looking into this problem. So the main reason is because PDL does not handle regions. So what we are looking at is create correlations between these two levels and then create a region-friendly eGraph representation. Yeah. And there are also other interesting open questions. So how do we handle operations with results? So if we look at most egg examples, we expect the expression will return a valid value, but operations like store does not return any value. So we could, like in traditional MIR, we could represent this as a non-value, but then we realize different non-values might represent different things, so they are not equivalent. So the other thing is evaluation. So once this framework is working, what's the best, or which compiler passes will benefit the most? Like there are many compiler passes available to be integrated into the eGraph, but which one will be super interesting? So particularly we have an example in a paper is taking functional inlining as an example. But it would be nice to explore them intensively across different passes. The other thing is application. So it's like how this framework can benefit different applications by unifying the completion and eGraph into the same framework. So we are looking at Herbie-like floating point optimizations and also like applications that require multi-level end-to-end completion. Yeah. That's everything. Cool.
Thanks for the great talk. Yeah, okay, great. We have lots of questions.
Thanks for the great talk. And one of the most important thing that a compiler must do when you use eGraph is to extract the best fitting instructions from the representation that you just described. So I think that is not clearly mentioned here. Can you clarify how would you implement the extraction?
Right. So extraction is a big problem for eGraph. I agree. So currently, I think we are still. So this project is like still at a very early stage. We are focusing on how do we represent eGraph in this IR. The extraction, currently the extraction is quite naive, just iteratively going through all the E-nodes and find the best one and extract. We haven't explored all the algorithms, but I guess the problem is the same for ACT, or other eGraph tools. So we can, if we have an algorithm, we can easily migrate to the MIR framework. Yeah.
So super cool talk. Thank you for giving this. And as the person who put EGRAPHS into crane lift, also very cool to see it, being integrated into IR in different ways. One thing that wasn't completely clear to me about your mechanism, you mentioned that CSE is used to do the E-class merging. So I can see how that works if you have two different definitions of the E-class that are exactly the same, right? But if you have like overlapping but not equivalent E-classes, so you have one E-class of A and B and another of A and C or something like that, which can happen if you like just merge in one of those values. Do you need CSE to be aware somehow of the semantics of E-classes?
So that's a good question. So I think at the moment we haven't observed this happening, and the main reason is because when we do rewrite explorations, I think it's currently sequential. So the E nodes are observed like incrementally, so we haven't observed that. So the key idea, probably like when we find this happening, then we will think about how to handle that. But our current implementation does not have this problem. Yeah. Thanks.
Thank you. I have a couple of questions, but I actually catch you after. But maybe the big question I kind of struggle to grasp is like, what's the main advantage you get of representing the eGraph as an IR, rather than just implementing this in C++ right next to, like in the MLIR framework, and you just do kind of X style, but you're not representing it. So what do you get by actually embedding the eGraph into the IR?
Right, that's also a good question. So the initial motivation of the project is like, it's cool, we should do it. And we haven't thought about this. Now we're thinking about this as well. I think the key benefit is like removing translation overhead. And in eGraph, so one thing that we think is quite interesting, but we haven't explored yet, is like in the eGraph, can we actually like using existing compiler analysis, so we can guide the search without translation and keep the equality information across, like maintain the equality information all the way rather than come back and forth. You can implement eGraph in Rust natively, that's no problem. That's another way of thinking about it, like implement all the compiler optimizations in Rust. But I think we haven't explored this yet, actually, yeah. So we don't know.
I think maybe a refinement of that question, which is something I had. It's like, what are you gaining by putting these eGraph operations in the IR versus like inside of MLIR, like next to the data flow framework they have, you add an eGraph framework, and then you can pull operations in there. Like, is this purely help out the implementation, or is like, what are you gaining by doing this?
Right. Yeah, it's a similar question. So I think these are the questions that we are exploring. So we don't know yet, because we haven't played with any other dialects as a case study or benchmarks yet. So the key, I think, what I have to thought about is like, there are different regions, there are different rewrites that's existing. It's mostly developing efforts. So it's like, it will take a lot of effort to use AG, but if this works, then you can probably just connect with any MIR framework or existing framework that helps, right?
Okay, let's thank the speaker one more time.
Thanks.
Okay, cool. Everybody hear me? All right, so I'm Cole Vick. So today I'll be presenting some work with Sammy Thomas. Sammy's in the back there. And so we worked on this project called Hatching Theory Instantiations with Yardbird, forgive the cutesy name, but this is about finding bounded model, or doing bounded model checking with EGRAPHS. So just as a general overview, I'll motivate sort of why we wanted to work on this problem. Then I'll talk about guidance in SMT solving. I'll give a bounded model checking example. I'll talk about how we use EGRAPHS, and particularly how we use EGG. We'll see a cost function comparison, and then I'll talk about conclusions and future work. So right, introduction and motivation. So as a rule, SMT solvers struggle with quantified reasoning, but quantifiers are, we want to use quantifiers to reason about things like arrays and distributed protocols. And so this talk is going to specifically focus on proving bounded properties of arrays in software. So the difficulty for SMT solvers lies in how they choose to instantiate quantifiers. And so the big question is, how do we know which terms are useful? And so we're going to tackle this by using user-defined cost functions or using the cost functionality that EGG extends to supply domain-specific information to the instantiator. So guidance in SMT solver. So SMT solvers generally allow syntactic guidance. Like in Z3, you can supply what terms you want to, or what terms you would prefer the underlying SMT engine to use in particular quantifier instantiations. But EGG's cost function framework allows finer grained guidance. So we can do sort of, we can do a semantic analysis of our terms, and it gives us finer grained control over which terms to instantiate with. And so the main point of this work is to compare Z3 with our tool Yardbird on bounded model checking examples. And so just generally, we can, the main takeaway is that our tool is faster than Z3 on 50 benchmarks, so we have about 200 benchmarks. And so we're faster than Z3 on 50 benchmarks, and it uses fewer instantiations on 94 benchmarks, which is about 50% of the total. So that's sort of the main takeaway, is that it really helps you in SMT solving to use, to have specific guidance in your problem domain. So here's the technique overview. So we're going to start with a Rust program. It doesn't have to be a Rust program. We just we have a macro system that translates Rust into our sort of logic language as VMT. And if you've seen SMT lib, VMT is very similar. Then we're going to abstract the array theory, since we're dealing with arrays. And I'll get into what exactly I mean by that in a minute. Then we're going to feed the abstract program into Z3. We'll get an abstract counterexample. We'll feed that into EGG. And then we're going to extract refinements, and again, I'll define all this a little bit later, but sort of the key is we're going to extract refinements with a particular cost function. So here's a Rust example. This is a very simple example of the typical types of programs that we're going to be doing bounded model checking on. So you can see this is array copy. We're going to take vector A and a mutable vector B and some loop bound in, and we're just going to copy the array A into the array B. And of course, we all know that this property holds at the end of this loop. So every index of A is equal to every index of Z. But how do we check this property? How do we verify this property? So we can do it in a bounded way using bounded model checking. And so the general framework is we're going to translate that Rust program into logic. We're going to unroll the loop in time. So if we want to do a bounded model checking to depth 20, we're first going to unroll to depth 1, 2, 3, 4, and so on. And we're going to check that the property is true at every step of the unrolling. So this is pretty simple to do in Z3 if you use the full array theory, and it's definitely simple if you are just trying to prove very small programs like the one I just showed. But it can take a long time if you're going to try to prove more interesting properties of slightly more difficult programs. And so what do I mean by the full array theory? So here are the axioms of array theory. So all these capital variables are implicitly universally quantified. And we don't have to go over exactly what these mean, but this is just kind of the general structure, and all of these will be encoded as rewrite rules inside of EGG. So abstraction and refinement in BMC. So how we can think about abstraction at sort of a high level is that we want to forget facts about the array theory using uninterpreted functions. So we're just going to forget all of the sort of interpretation of the array theory, and we're just going to use uninterpreted functions, and we're going to sort of add back in only the facts that we want the solver to know about. So we're going to worry about instantiating those quantifiers. And of course, this removes the need for quantifier reasoning in the SMT solver, at least at the array level. And so yeah, what I mean by refinements are just array axiom instantiations using program terms. So we can see like this is an example of an instantiation that EGG might find in a typical bounded model checking loop. So refinement generation. So yeah, so this is now kind of getting into how we use EGG. So we're going to build the EGRAPHS in EGG from the SMT solver model. So we're just going to put all the interpretations of the variables, all the interpretations of the program terms into the EGRAPH. We're going to saturate the EGRAPH with the array axioms. And then, so this is kind of a weird way to use EGRAPHS. I don't know if this particular thing is usually done, but separation will stop if two E-classes will be merged by a rewrite. So we don't want to start merging E-classes after the original EGRAPH is built. And why we don't do that is because this signals a gap in solver subtraction. So if we're going to use an array axiom to merge two E-classes, that means that our original Z3 model didn't know about that particular fact of the array. Here's what we're going to add it back in. And so we can just immediately use that rewrite that EGG gives us, but we're going to, there's no guarantee that that refinement is going to be good. So there's these raw refinements that come out of the EGG are not guaranteed to be useful. They might be useful, but we're going to minimize the refinement cost using the custom cost functions. So we're going to use cost functions to prefer, quote unquote, better terms in refinements for some definition of better, and I'll get into what I mean by better on the next slide. But yeah, so again, EGG's cost function framework allows us fine-grained semantic control. So we can do things like, look at a term and, compare terms with other terms in the model and, do sort of fine-grained control on this particular, problem domain. And so this differs from traditional SMT solver term selection in that we're not just going to pick from a static bag of terms. We're actually going to, sort of do some sort of semantic evaluation of them in the cost function. So I used two cost functions in the evaluation. So the first is AST size. So this is just a very naive implementation of a cost function. We're just going to prefer small terms to instantiate those quantifiers. And this is likely going to miss opportunities for generalization. So to kind of get a sense of this, you could think that we might instantiate a quantifier with the constant term 0, where actually we would want to use some more complex term like selective A at some particular index. And that's going to be the key to allow us to move forward in the proof. But with the AST size, we're just going to plug in the smallest possible term, and we'll likely diverge at that point. And then we have this slightly more complex cost function called the property-directed cost function. And so this prefers terms that are in the property check or that are later in the bounded model checking trace. And this is likely to miss important constant terms. Small constant terms we'll probably forget about. But since it leverages the problem structure of a bounded model checking problem, it's likely that it will perform better, and we'll see the results bear that out. So here on the left-hand side, we have Z3 runtime on the x-axis, and then we have Yardbird runtime, which is our tool, on the y-axis. So we can see anything below the x equals y line is where we do better. So you can see for AST size, for that naive cost function, we're doing pretty awful. Z3 is sort of dominating us on all of these problems. And then here is a graph. Instead of runtime, I've plotted the number of axiom instantiations that we had to add and the number of axiom instantiations that Z3 used to prove the same property. So again, Z3 is using fewer axiom instantiations than us, and it's beating us on all these fronts because we're using this naive cost function that doesn't leverage problem structure. But when we have this property-directed cost function, you can see that the runtime cost is getting much tighter around the x equals y, and then for this particular for this metric of number of axiom instantiations needed, we can see that we're actually starting to outperform Z3 by quite a large margin on about 50% of the examples. So it's kind of interesting. And kind of to give some sort of rationale for why this metric was included, I just thought it was kind of interesting to include something where we can actually see some improvement over a super highly engineered SMT solver like Z3's, because we didn't do much optimization on our tool, but we were still able to see we were able to beat Z3 on about 20% of those benchmarks, and 50% when we used this kind of maybe a little bit contrived metric. But yeah, so the conclusion is that user-defined cost functions can beat Z3 without optimization. Like I said, we did not try to optimize our tool, but we were able to beat Z3 on some number of examples. And we can see that property-directed is better than AST size for this particular. I mean, that's kind of unsurprising because we're leveraging more problem structure. But there are still cases where AST size dominates property-directed, like for one particular example, this array split 11. The property-directed cost function diverges. It chooses some term that it shouldn't have, whereas the AST size finds a small proof for a bounded depth. So these are still just heuristics. It's not a one-size-fits-all solution. You're still going to have to care about, different cost functions for different problems. So future directions, yeah. So further improvements to cost function guidance. So just trying to make better cost functions for these problems is kind of an interesting area, trying to, beat Z3 on a larger number of problems. And then dealing with other theories is also interesting. Abstract data types specifically, we could kind of do bounded model tricking on more problems, on a specific problem domains. That would be interesting. And then integration with inductive invariant generators like IC3IA. So we could extend, so we could do a bounded proof up to some depth, and then using the instantiations that we found to get a bounded proof, we might be able to supply guidance to an unbounded proof generator in the case of inductive invariance. And then we could integrate history and prophecy variables. This is some of my previous work that this is kind of a quantifier elimination technique. But I haven't implemented that yet in Yardbird. And then also, I was thinking it might be interesting to supply guidance to theory explorers like Enumo. I don't know if this is totally off base, but it would be kind of interesting. If we found a rewrite in Enumo, maybe we could try bounded model checking with that rewrite, and so I kind of prefer rewrites that allow you to get further in bounded model checking. But again, I'd love to be corrected by that if someone knows more about that than I do. But yeah, thanks, and happy to take any questions.
Thanks for the great talk. We have plenty of time for questions.
Yeah, thanks for the great talk. Can we go back to the summary?
To the what?
To the conclusion.
Oh yeah.
Okay. So if you during your design of the cost function, what was the most important thing you have to consider to apply to the cost function? Which information was the critical part of the
Right. So, it obviously helps to have experience with bounded model tricking problems. So, in proofs, it's just likely that terms that appear in the property will be helpful in proving that property. And so that was kind of the most key thing, is to prefer those property terms in your term selection when you're instantiating quantifiers. But, there may be other things. I haven't fully explored that. Yeah.
Do you think there is a kind of a universal cost function that can help everything?
Definitely not. We saw that even this AST size cost function will beat property directed on some amount of the problems. It's just the problem is too difficult. The search space is too large to have a one size fits all cost function. It's just not going to.
Could we imagine a system that can evolve the cost function automatically from the simplest one like AST to fine-grained?
I think you definitely could. Another thing I thought about was kind of running cost functions in a portfolio sort of way, and just sort of, picking the best instantiation. Or I guess now you have to have a second order cost function to pick the best instantiation from the cost functions. But you could just run them in parallel and just say, if this particular cost function, happens to find a proof, then that's fine. And if another one does, that's also fine.
Okay, thank you.
Hi, given a problem, can you typically decide if your tool is going to work better or if C3 is going to work better, so you can build a portfolio solver?
Right. So I think, when we look at something like this, I was trying to find some sort of pattern in the problems where you could say, this particular problem is definitely going to work better on our tool, and then this other problem is going to work better in Z3. I wasn't able to do like a full analysis of that, but one thing I did notice was if there's theory combinations. So if you're doing a lot of multiplication in the loop, and they have all these array tiling examples where you're doing something like that, then the abstraction of the array theory kind of helps Z3, from my experience, kind of explore that theory space. And then, just by supplying, maybe a few array instantiations, you might be able to find a proof faster. But I've also seen the converse. So I haven't been able to draw a strong conclusion about when this technique will work or when it won't. That would definitely be an interesting thing to find out.
Great talk. I wondered if there's something special about the theory of arrays that caused you to focus on that, or would this work for bit vectors, or choose your favorite, some other thing?
Yeah, I mean, I was just familiar with the theory of arrays. Some of my past work has been on that, and I had this nice benchmark set that allowed us to kind of, get some examples running quickly. But I think so. It has to be axiomatizable in this sort of, like the theory of arrays is nice just because it has a very small axiomatization, and that like these are very easy to encode as rewrite rules. So like in the theory of bit vectors, I'm not sure if you could. I mean, I don't know for sure, but yeah, I don't know if it's as easily sort of translatable into this. But I mean, that would be. I mean, that's kind of what I was thinking about with like ADTs. Is maybe there's some way to encode the problem like that, but I don't know.
Okay, let's thank the speaker one more time.
I'm Andy, and I'll be discussing our work on automated high-level synthesis, design modulation via EGRAPH anti-unification. This work was done while I was at Georgia Tech. And yeah, let me just get straight into it. So I'll start by giving some background and motivation on what hardware design with high-level synthesis even looks like, the importance of design modularization, and then dive into some background on what EGRAPH anti-unification even is and why it's particularly useful in this case. So for those of you who aren't too familiar with high-level synthesis and hardware design, high-level synthesis, commonly referred to as HLS, basically can convert input programs written in a high-level language, such as C++, into actual hardware. And this hardware directly accelerates the exact function or like purpose of your program. So this is what this kind of flow looks like. You have a function or a set of functions written in a high-level program, and then you get an accelerator computing that. So then you can obviously do this for many different programs, each one synthesized into its own accelerator. So the main thing I want to highlight here is that how you write your input program directly influences the quality of your hardware. So the code structure in C++, namely your loops and functions, directly determines the properties of your hardware. So some things you can see here is like when you have a loop, you just instantiate your functions once, and you're going to repeatedly call them. Whereas if you have like an unrolled loop where you have multiple instantiations of a function, you get many functions acting in parallel. So obviously, in this case, we have 3 input programs, and we're generating 3 unique hardware designs, 3 unique accelerators. However, you might have noticed I used the same functions, f, g, and h, across all 3 input programs, and we've basically instantiated them many different times across the different hardwares, even though we're using the exact same hardware modules. So this is a property of our modern HLS tools. That's how they were designed. And this basically makes them really good at automatically synthesizing accelerator hardware. You can write an input program in C++ and then automatically generate the accelerator for said input program. However, this is not really good for synthesizing architecture hardware. So what I mean by architecture hardware is if you think of your traditional CPUs, GPUs, when you have an input set of programs, they all run on the same set of hardware. You don't get 3 separate instantiations. But as we can see, HLS isn't really optimized for that. And that's due to, you would have to write your input program itself describing an architecture as opposed to just a function. And then this kind of interacts with how our modern workloads look. So AI and ML workloads have like really benefited from custom hardware recently. And they're constantly evolving, your ML models. However, they constantly reuse the same key operations. So this includes like your gems, your convolutions, your attentions, and your activation functions. So our hardware is the same across iterations, but if we were to use HLS, we're constantly generating new sets of hardware, even though we're basically doing the same thing. And then AI and ML workloads and other modern workloads have shown to benefit from highly specialized architectures as opposed to really, really specialized accelerators. And then finally, so what design modulation really is it forms the basis of what's in an architecture, because if you modularize your design, you determine what are the common compute units, and these are going to be the basis of your architecture. However, in both high-level synthesis and traditional hardware design, it's highly manual, tedious, and then therefore error-prone. So you need to determine what is going to be a common module, how you're going to use it in each of your programs, etc. So really, this becomes an issue because HLS's original promise was it's going to be easy hardware design. It's going to be much easier than RTL. You just write your programs, and we're going to give you good hardware. However, right now, it's just as difficult as RTL to go and modularize your design, and you have to do a lot of manual work. So we're really failing on that promise. And what I want to highlight is for HLS to continue to deliver on said promise, we need to support this automatic design modulation. We need to be able to determine a set of common modules for an input set of programs that's going to form a common architecture, something like this diagram on the bottom right. The next generation of HLS flow should take in many input programs and then determine the best common architecture for these input programs. And that's exactly what we want to show in this work. So on the left, you have our current HLS flow. On the right is the next generation that we envision. And to bridge the gap, really what you need is a way of doing automatic design modulation. You want to find out what are the common functions shared across our input programs, put these into an architecture, and then run these P1, 2, and 3 as instructions over this architecture. And that's exactly what I'm going to focus on in this work, is how we perform this automatic design modularization. And spoiler alert, it uses EGRAPHS. So a few years ago, by some of the members in this audience, they developed a tool called Babel. And what Babel does is explores library learning via a programming languages technique called anti-unification. And by library learning, that means when you have an input set of programs, you're exactly doing learning common functions that can be used across the input set of programs. What anti-unification is if you have some expressions, it's a way of determining a function abstraction over these expressions. And equality saturation can really help in this case because you can expose many equivalent representations of your expressions to find better or more general functions. And in Babel's case, so they provided this framework that can do the eGraph anti-unification, and it was highly motivated by program compression. So finding a common library which minimizes the overall program length. And then we want to basically take these same ideas of library learning and apply them in hardware, because when you find hardware common functions in your HLS designs, this is going to equate to a common hardware module in an architecture. So step one is to actually explore equivalent representations of our input HLS designs so that we can learn useful hardware modules. So that's step two, is learning these actual function abstractions. And then step three is when we have a function and then a modularized implementation, we need to select the best one for our hardware. So as I mentioned, the first step is really exploring the HLS design space. And HLS is particularly, loops are a very common structure in HLS. So I'm going to basically be going over how we analyze loops and explore loop transformations. So let's say we have our input design over an IR in the eGraph, and we have a bunch of loops. So common loop transformations are like loop unroll, loop reorder, loop tiling, all the ones you're familiar with. But you also might know that you can't apply these to every single loop. There is some validity check. So we do need our loop transforms to preserve equivalence. And primarily for loop unroll and loop reordering, this is due to the memory accesses. And luckily, there is a technique for finding out when loop transformations are valid, and that's using something called polyhedral loop analysis. So we're going to use that to try and determine the validity of unroll and reorder before we go and apply them. One other issue, as many people have talked about today, is the scalability of our eGraphs. When you go and try apply every possible loop transform to every possible loop, you're going to blow up your eGraph, you're going to run into a scalability wall, and you're going to kind of prevent anything useful happening. However, in this case, when we explore the design space, it's not to optimize our program. It's more to find out which loops are similar and can match so we can find a useful function abstraction. So it'd be really useful if we could know that beforehand and only apply the transformations there and not blindly. And luckily, so that's exactly what we want to do. And luckily, polyhedral loop analysis also provides a technique for doing this, or at least the structure does. So we're going to use that to find similar loops and then conditionally apply these rewrites on those loops so we don't continuously blow up our eGraph. And I'll kind of get into how we do both of these things. But before that, the key part of polyhedral loop analysis is the polyhedral representation of our loops. I don't know how familiar the audience is with this, but basically you have a domain for like a nested loop, and this is the space for each of your iterators. It's just effectively your loop bounds. And then you also have a map which says how the iterator space maps to memory accesses, both reads and writes. So let's get into the first step, which is how we're going to use polyhedral loop analysis to determine the validity of our unroll and reorder rewrites. There's many libraries that can do polyhedral loop analysis for you. We use the integer sets library because it's like kind of agnostic of your input language that your loops are represented in. And they have an object and a method called the ISL schedule. And the ISL schedule contains exactly the information we need, which is permutability, which tells you whether a loop reordering is valid. And it contains a term called coincidence. And what coincidence is tells you whether a particular loop can be unrolled or can't. So in this given example, we have a simple for loop here computing a matrix multiply. Your domain and schedule are fairly trivial in this case. It's just the loop bounds. But then the ISL schedule object correctly identifies that this nested loop is permutable, as you can see. And then also the coincidence in this case is 110, which means that loop MMI and MMJ can be unrolled. There's no dependency between each iteration. But loop K can't, and that's due to the accumulation over that dimension. So we're going to use this information for our rewrites. Before I get into that, I'll also talk about how we're going to use the polyhedral loop analysis to address the scalability issue of only finding loops that we know are similar. So to do this, we introduce a structure ourselves called a loop group. And what this loop group is, it contains loops that have the same memory accesses after some permutation of the iteration order. And we're basically going to use this to find out which loops we believe are going to be similar because their memory accesses are similar. So what this looks like, it will help with an example probably. So on the right, we have two programs, each having their own implementation of a matrix multiply. There are two programs that are almost identical, except that the loop we do the accumulation over, K and P1 and Z and P2, are in two different spots. They're swapped, MMZ and MMY are swapped in P2. So we know these two programs are equivalent, and we basically want to try and match these two loops. So the first thing we need to do is compare the memory accesses in our loop. And thankfully, the polyhedral representation has this easily available to us. And then we're basically going to use that to then permute different orders and see if these memory accesses match. And that's exactly the next step. So as you might have intuitively noticed, and as I mentioned earlier, these two loops are identical and do have the same memory accesses once we permute MMZ and MMY. And that's exactly what the mapping in the loop group is trying to show. MMI in this case was the first loop, so it's kind of identity. But then MMX highlights that you need to swap loops 2 and 1. And then this mapping is exactly the reorder we need to match these two loops. And it also highlights which loop depths match. And therefore, we're going to search for tilings over these matched loop depths. As this would suggest, there could be a common function here that we might want to take advantage of. So summarizing all of this into how this builds into the eGraph and the rewrite flow, this is the top path when we take advantage of the integer sets library. We create an ISL schedule, and then we extract the unroll validity. And then we're effectively going to create a dynamic rewrite for loop unroll, which is only applied when this unroll is valid. Similarly, you're going to take the polyhedral representation, create a loop group, and use this to determine the order mapping we're going to need for loop reordering. And again, we then add in the reorder validity from the schedule with the reorder permutation, and that tells us when we want to actually apply loop reordering to loops in our input program. And finally, you then take the order mapping, and then here we're determining a tile size using the greatest common denominator of our domains. And this is basically guaranteeing we're going to find a common loop that can tile both. And then this tile size goes into the loop tiling rewrite. So these three rewrites are then going to be just applied over our input space, and we're going to explore not an insane number of loops, only the ones that we know will match. So once we have this space, we now need to get into how we actually perform the hardware module learning. And this is the main section, which is going to use Babel. So as I mentioned earlier, Babel does do library learning over our eGraphs with anti-unification. So the question obviously arises, can we just use it? Can we just plug in our HLS designs? And can we extract really good hardware? As you may have suspected, the answer is no. And that's mainly because minimizing the program length doesn't correlate with really good hardware. And the main reason for this is good hardware needs two things. One, it needs to be synthesizable. And what I mean by that is not every C++ program can actually be converted into hardware. So we need to make sure we can do that. And then we also need really good hardware performance. And this is power, performance, and area, typically referred to as PPA metrics. So we also want to make sure our final design optimizes this as opposed to some notion of program compression. And obviously, this then leads us to the next step. We want to adopt Babel and adapt it to use hardware-oriented cost functions. So before I get into what our cost functions are, let's try and summarize exactly what we want from our designed hardware. So number one is you want your modules to be synthesizable. You want modules to be meaningful. This is inspired by, in traditional computer architecture, each compute unit has a purpose. It means something. It's not just arbitrary arithmetic functions. And you want it to be holistic. I'll kind of get into why this is important, but you basically don't want to be splitting up functions that do this, that are highly related. Number two is that we need to ensure that the final hardware design actually optimizes our PPA metrics and not abstract notions of meaningfulness or holisticness. So again, a simple example here should help. In this example, where you have two programs, each computing a dot product, one of length 8 and one of length 24. And I've given three different ways of how you might do this in a hardware module. So example one has no modularity. Program one does its dot product, and program two does its. Program two uses a common module, which is the multiply accumulate. And then both dot products can use that. And then program three actually has a dot product as its common module of length 8, where program two then tiles this 3 times to compute its dot product. Obviously, we can compute a bunch of different costs here for arbitrary cost functions. And in this case, the three that we're going to be comparing is the Babel cost. So this is the naive program length cost over our eGraph. And then the other two are introduced in this work. And this example is going to hopefully motivate their existence. So the first is the hardware impact cost, and the second is the hardware performance cost, each trying to target requirements 1 and requirements 2 respectively. And we'll kind of get into where they come from and why they're important. So let's analyze. And then, yeah, before we do that, the thing you need to recognize in this example is the no modularity case. They each optimize a different cost. The no modularity case is actually minimizing our program length. The middle case minimizes our area. And the final example is minimizing the hardware impact cost. So when we think about the no modularity, obviously there's no shared hardware module. And this is actually failing both requirements. So no module, you fail requirement 1. But then because you didn't find a hardware module, you're actually reusing the same functions multiple times, you're wasting area, and therefore you're failing requirement 2. So clearly this isn't a good cost metric to optimize for hardware. In modular 1, I would still argue you fail requirement 1. This is because you're not capturing the full dot product. So while it's synthesizable and meaningful, it's not particularly holistic because you're separating the operation. And the reason this is really important is while the produced hardware is hardware friendly, it does minimize area. By separating the operation from the loop, you can't perform loop optimizations here, and then you can't minimize your delay even further. So I would also argue that this isn't particularly optimal. Which leads us into modular 2. So here, the shared hardware module is our dot product. So it is synthesizable, it's meaningful, and it is holistic here, capturing the whole operation. And then therefore, when you capture this whole operation, if you want to go unroll this loop or perform further optimizations on this loop, it exists in the function, and you can further optimize your PPA. Hence why, in this case, both your hardware impact costs and performance costs are minimized. So how do we, so what does this teach us? Is that we actually want to decouple the stages and our cost functions. We want to find out which hardware modules to use by using the hardware impact cost, as this kind of targets when hardware requirement 1 and which modules are very useful. So that's what this looks like. It's like which modules should exist in the shared hardware. And then we're going to use the hardware performance cost when we have an explored eGraph with function modules to then extract the design. And this is basically equivalent to telling us how we want to implement these shared hardware modules and what's the best way to minimize PPA. So let's get into what these hardware cost functions actually are. So we have the hardware impact cost. What this does, the key takeaways here are that we assign a cost of 1 to every arithmetic and memory operation, no matter how expensive it actually is in hardware. More to just kind of a notion of it's one hardware operation. So some abstract notion of importance. Our for loops are proportional to the number of iterations they take, and then the cost of the body. Two things we do here is that variable bound for loops are given an infinite cost. That's because this isn't particularly synthesizable or hardware friendly. And similarly, if the loop body doesn't use the iterator, we deem this not to be a very useful hardware function. So those are also given infinite costs. The costs of our functions is just the cost of the arguments, ignoring the cost of our primitives, because when you implement them in hardware, those don't really serve any purpose. And then when we recurse over the eGraph, this is almost exactly as it's done in Babel, where we count the cost of the function only once, as a hardware implementation will only instantiate a function once. So the hardware performance cost is a weighted sum of the area and the delay. I won't go too much into this, as this is basically just proportional to the gate costs. But the main thing here is that, I guess, delay, when you recurse over the eGraph, uses a maximum recursion, whereas area is more similar to just a sum. And again, you only account for functions once. And this summarizes, I guess, both cost functions, and I guess there's more in like the paper. But the two most important things here is that the captured metric by our hardware impact cost is synthesizability and trying to be important, which is proportional to the number of hardware operations taking place. Whereas the hard performance cost is a better model of PPA, trying to capture both hardware area and hardware delay. So let's get into some of the results. So, and like, does this actually work? And the answer is yes, to some extent. So this is just some examples of automatic modularization. In blue is input HLS designs, and then in green it's the output of our tool, which are all modularized, where the module highlighted in red is shared across the output designs. So we're able to do this over arithmetic equivalences, loop on roll equivalences. The case on the left is kind of interesting, which where program 2 has a dot product, and program 1 is a complete matrix multiply. And as we know from math, you can actually compute your matrix multiply using just dot products. And that's exactly what our tool can automatically identify in the output. Continuing along this line of reasoning, we have a loop reorder case as well, where you're learning common functions over this reorder, and then a tiling. And then probably the biggest case we handle right now is a matrix multiply tile. And what this is you have two programs, each computing a matrix multiply themselves of different dimensions. And then you're going to find a common tile that can be used to compute both matrix multiplies, significantly reducing your area. So that's what this table shows, is just the area change after modularization. I'm not really showing this to like point out any significant area saving, because this is quite obvious. If you share hardware and you use less, you're going to use less area. But it's more to highlight that we can actually automatically identify the shared hardware module reuse. I also don't really mention delay or power, and that's because until we have a proper way of executing these designs with sharing and a proper way of scheduling and executing, the performance and power estimates from HLS don't really make any sense. So thankfully, one of my lab mates is working on that problem itself. One thing I want to really highlight is in previous iterations of this work, and actually in this diagram, there's only 2 for loops for our matrix multiply tile, so it's actually not complete. And that's because before we introduced polyhedral loop analysis, we actually couldn't, because our eGraph was way too big. We couldn't identify the proper common function. And we used to take 180 seconds to not even do that. By introducing polyhedral loop analysis, we've really solved the scalability problem, finding the complete tile in only 20 seconds. And then the last point here is that we can do this on GEM, general matrix multiply, which is already a very useful and common operation in your ML, in the ML world. But also other ML operations are just nested loop operations, such as convolutions, attentions. So this similar idea of tiling and reuse can be exposed there. And then finally, just before I go, I want to highlight some future opportunities that architecture-oriented HLS tools are going to open, we believe. So this is mainly to do with architectural DSE. So imagine you wanted to create a hardware architecture. You had a couple of programs you want to run. So let's say it's 2. You have A and B. So you can just create the most optimal architecture for these 2 input programs, highly specialized and flexible enough to run either one. But then you come along, and like next week, you have program C. You're like, OK, I also want to execute this. So now you want to create the best hardware architecture for A, B, and C. And you keep doing this, so D, and you can keep adding as much as you want. Obviously, the more programs you run, you have increasing flexibility of your architecture, but you're also increasing its overhead to be able to run each of these separate programs. And really, you want to ask the question, like, what is this trade-off? Which of these architectures is ideal for my use case? And having a tool which can automatically generate an architecture based on an input set of programs that's highly specialized to them is going to be critical to exploring this question. One other potential architectural DSC we want to highlight is in this work we do tiling, like when we tile stuff, we use what I like to call a minimal tiling with the greatest common denominator. So it's the smallest matrix multiply that can tile both operations in this case. But you can also do a maximal tiling, which is the lowest common multiple of your loop domains. And in this case, you're actually creating the largest possible matrix multiply tile that can fit both operations at the cost of not using some of your hardware in either case. So you have really high area, but as a result, you can execute the matrix multiply in one cycle as opposed to 8 or 2. And again, which of these common tilings is ideal? Highly dependent on your use cases. And again, being able to automatically generate these architecture is really critical. So this is mainly just to highlight the point that these architecture-oriented HLS tools are super important for the future of architecture and hardware design. Anyways, that's the complete talk. Thank you, and I'll take any questions if we still have time for that.
Thanks for the great talk. This session is, ending ahead of schedule, so we have time. We have a nice buffer before lunch for plenty of questions.
Hey, thanks for the great talk. This is Rachit from MIT and Jane Street. I was curious, so in HLS, oftentimes when you actually want a high-performance design, you're going to use a lot of pragmas.
Yeah.
And unrolling is one of them, but really you want to be pipelining your design, you want to be banking your memories. And so really what you probably want to be able to do is have some notion of a context under which you can extract this loop, right? If you have a loop that is in parallel accessing some memory and the memory is not going to give you the kind of bandwidth you need, the parallelization is useless. So I'm curious if you've thought about having some notion of a context under which this anti-unification abstraction actually makes sense, and how to include things like pipelining, which are not source representable because they're sort of a weird optimization that happens at the hardware level. Thanks.
Yeah, thank you for the great question. Yeah, so this work is basically quite early stages. It's just, we originally wanted to ask the question, can we even do this? Can we find useful hardware modules? Which is what motivated this work. But yeah, you're absolutely right. HLS has all these pragmas, and different optimizations make sense under different scopes. So in my opinion, like a context does make a lot of sense. And this is probably going to go into like your cost function. So under different contexts, unrolls make more sense. Maybe if you have pipelining, you don't want to do that. So I think it is a kind of an open challenge of how you want to incorporate pragmas into the design space and use that to extract. But that's definitely kind of along the lines of this, but even just general HLS optimization in an EGRAPH setting. But yeah, so right now, we haven't really considered it, but definitely future iterations of this work, it is on our kind of to-do list. Thank you.
Hi, it's Dennis from Google, and basically a question I have is at some point you have this concept of meaningful design.
Yeah.
And I was really confused, why do you need that? Because my assumption is you have some costs, maybe they're imperfect, but you really care only about performance. You don't really care if it's meaningful. So why do you need this concept of meaningful design?
Yeah, so basically what kind of motivated that was, I guess it's kind of back here. Yeah, so what we are trying to incorporate with meaningful is we were running into cases where you don't really learn something, you kind of learn something arbitrary, and then it's not actually able to be used very effectively later on. And basically what the meaningful here comes out as is just the number of hardware operations. You don't really care when you learn a hardware operation, like how expensive the operation is to an extent. You want to learn like just the most operations in a module. So that's where that's coming from. And I think it's just more motivated by, so if I have programs A and B, and then you just learn the best, it'll be best for A and B, but we hope that like part of the motivation for this is like when your ML model changes every year, you can still hopefully be able to run it on the same architecture. So being able to extract something a bit more general than just the most optimized, we believe makes sense. But yeah, there does need to be, I think again, a big part of a future direction of this is a big analysis over our cost functions, because we do believe that's like super critical to finding the best architectures. So there is like going to be a huge, kind of like a bigger cost function study of like how do we design the best hardware.
So is it kind of similar to like overfitting? Do you feel like you try to fight overfitting on the inputs you were given?
Yeah, it's exactly that.
Okay,
Yeah,
perfect.
it's exactly that.
So I thought the incorporation of polyhedral analysis to kind of find common loop, I guess unify loops somewhat was very cool. And you're kind of doing that outside the eGraph using this ISL library. This is maybe a vague question, but would it be valuable to be able to represent the loops and various tilings or reorderings within the eGraph?
So actually, the loops are represented in the eGraph.
Yes, but your reorderings, et cetera, you're doing that externally, right?
So, kind of. So we kind of find the reorder externally, but then we have like the loop reorder rewrite is performed on the eGraph. So we have both the original loop and then the reordered one exist in the eGraph. I don't know if that's answering the question or.
Let's just chat afterward.
Okay, yeah, that makes sense. Thanks.
Oh, check. And thank you for the great talk. So it is very interesting to use library learning to learn common architectures. So I have a question about this part. I think one limitation of library learning is that it has a very high requirement on the similarity of the input programs, right? So if you give it a large set of programs, then it may be disturbed by small commonality between a large part of programs instead of a large commonality between a small set of programs. So have you discovered similar problems in your use case? For example, have you tried to put all your programs in all case studies into your approach at the same time and see whether it can learn all the architectures in all case studies?
So no, we haven't quite done that yet because up until like 2 weeks ago, we were really bottlenecked by the scalability. So as soon as we tried to do multiple designs and each one having, let's say, multiple possible functions to learn, the tool would just break. So we're hoping to be able to explore some of that soon. But I can definitely see that being an issue here. And I guess it comes back to like your cost function question of how you want to address what is a good library. Do you want it to match all your input programs, or do you want a really big one across like 2, but not the rest?
Okay, let's thank the speaker one more time. And that's all for this session. So we're done, I think, 20 minutes early. I think there is lunch at noon, and we will resume here at 2 p.m. questions, we should have some time to do that as well. So yeah, please take it away when you are ready.
Okay, cool. Hi everyone, thanks for being here. My name is Paul. I was an undergrad at UCLA. I actually just graduated like a couple days ago, so not quite accurate anymore. But this work was done with my advisor, Professor Remy. He is the reason why this work was able to be completed and provided like so much helpful advice and guidance. So big thanks to Professor Remy. Not here today, but he is here with me in spirit. Great, so just as a very quick recap of what EGRAPHS are. EGRAPHS, you can kind of think of them as like a list of ground terms. So like for this really simple example, it's just like a times 2. And then you see that the sort of like the leaf e-nodes are represented in yellow here, and then we have like a multiplication e-node, and the classes are represented by the boxes that they reside in. The nice thing about EGRAPHS is that you can add more ground terms to the eGraph using rewrite rules. For example, in this case, we apply strength reduction, and a really cool, neat feature of EGRAPHS is that it does term sharing and some other ways to reduce the size of the eGraph. In this case, we only have these 5 e-nodes in order to represent these 2 ground terms. Now, a big problem with eGraphs is that with certain rewrite rules, especially associativity and commutativity, they tend to explode and grow in size very rapidly. So let's run through a quick example of that here. So let's start again with a ground term. This time it's a times 0. And then let's consider what happens when we apply 2 rewrite rules. The first one is just multiply by 0, and the second is associativity. So let me try a live demo. So this is just basically the eGraph that we had before, or rather the rewrite rules that we had before. And then we can see here that we start out with the same eGraph we had. It's just a times 0. And then if we are to apply these rewrite rules once, then we end up with this eGraph. And you'll notice here that only the multiply by 0 rewrite fires. And so we end up with an eGraph that represents the term 0, but also represents a times 0, but also represents a times a times a times a times 0. One nice feature about eGraphs, at least as they are implemented in EGG, which is the state-of-the-art library for representing eGraphs, and which is like will be the focus of my talk. A nice feature about eGraphs is that they can be self-referential. So in this case, we have like a bit of a cycle here. So it actually represents infinite terms, which is pretty cool. Now, as we continue running these rewrite rules, we see that the eGraph gets bigger, which is sort of what's to be expected. But you'll notice, rather concerningly, that as we continue applying these rewrite rules, the eGraph starts to get bigger much faster. And even just by the 4th iteration, we end up with this like big mess of spaghetti. And then if we get impatient and then try to run the iterations a few too many times, it's going to end up having way too many nodes. And then, at least in this browser demo, it's not able to represent it. And so if we go and like take a look at the logs, and we go all the way down to the bottom, oh, it looks like it hasn't quite crashed yet. There we go, now it's panicked. You'll see that our final eGraph size ended up being like multiple thousands of e-nodes large. So that's not quite great for eGraphs, because the whole like sort of deal with eGraphs is that you want to be able to efficiently represent terms. Now, there's been a few proposals for addressing this problem. At least in EGG, there's a couple strategies that have been used. The first is scheduling. So you can control like when rewrites are applied to the eGraph. The default scheduler in EGG is known as backoff scheduler. It uses this like nice little exponential backoff algorithm that basically bans exploding rewrites, gives the other rewrites a chance to catch up. Another strategy that has been used in EGG, at the very least in its math.rs test suite, is pruning. So let's say we have this like eGraph here. You might recognize it from before. It has a root e class, and the root e class represents a whole bunch of different things, but also represents just the number 0. Now, the nice thing about this is that because it just represents the number 0, you can kind of like ignore all the multiplication e-nodes and then just like get rid of them, and then you end up with an eGraph that just represents 0. So that's pruning. And in the course of this project, I discovered that there is a bunch of other strategies that people have used to address exploding eGraphs, which I think speaks to like how important the problem is. One of them is what's known as inverse transformations. The concept behind this is a bit abstract, so here's like a good example. So let's say that we have like a list of numbers, and then we like take their sum. This is actually equivalent to just taking the sum over the numbers like sorted. But you'll notice that the inside list, the 3, 2, 4, 1, 5, is not equivalent to range 1, 6. But because the sum operation is applied to them, the order is actually does not matter in this case. So with inverse transformations, you can basically consider the inside list as if it were sorted, and then you can apply rewrites to the eGraph with that knowledge. Another strategy is that you can reinitialize the eGraph with the best extracted term. So in the course of equality saturation, maybe once your eGraph gets really big for some arbitrary definition of big, you extract the best term from that eGraph, you throw away your eGraph, and then you start anew with a new eGraph. And then another technique that I've seen is what's known as guided equality saturation. This one's pretty interesting. Let's say like you want to like write some kind of proof, and you know sort of the intermediate steps of that proof, but you want equality saturation to sort of fill in the gaps for you. With guided equality saturation, because you have these sort of intermediate terms, it allows you to complete equality saturation without running into the explosion problem too much. So with my talk, I want to introduce the idea of destructive rewrites. And with destructive rewrites, you want to take the existing rewrites that you have for your equality saturation, and then you want to automatically keep the eGraph small with those rewrite rules. So with my specific implementation, the way I did this is that for every single rewrite rule, we ematch on the left-hand side as usual. But instead of adding instances of the right-hand side, we actually remove instances of the right-hand side. There's a few other ways you could do this. Like one way you could do this, for example, is that you ematch on the right-hand side and then you remove the left-hand side, which might be more interesting. But just for this talk, we'll be focusing on this particular implementation. So let's run through a quick example. So again, pulling up the eGraph that we had before, let's say we wanted to undo the associativity rule. So we ematch, and then we figure out like what E classes A, B, and C correspond to, and then and then we can pick, say, like that E node on the left there, that's boxed in pink, as sort of like the top E node that represents our left-hand side. And then when we take a look at like what E node might represent the right-hand side, we might end up with this E node. So with destructive rewrites, instead of sort of like adding that E node to the eGraph, we would actually want to remove that E node. So in this case, we remove the E node, the multiplication E node from the eGraph. One caveat is that the way that eGraphs are currently implemented in EGG, you don't really know like which rewrite an E node came from. So even if that E node was added by like a different rewrite, we're still going to remove it because it like matches the right-hand side. So that's a caveat to keep in mind, and I'll discuss that limitation a little bit more later. And once you remove your E node, you want to be careful to clean up your unreachable E classes. So like in this example, right, that multiplication E node is the only pointer to the E class that's boxed in pink. So we're going to want to make sure to clean that one up. There's a couple other things you need to be aware of with destructive rewrites. The main one is that besides clean up the unreachable E classes, is that the eGraph must always contain at least one grounded E class at the very end. Grounded basically just means that you can extract a term from it, so it still has to have like one of the leaf E nodes at the very end. So let's take this eGraph right here. There's just 3 E nodes in it, but we're interested in this plus E node right here. And with this eGraph, if we try to remove the plus E node, what we'll end up with is an eGraph that just has this function f pointing to itself. And so you'll end up sort of like with an infinite term. You'll end up with like f of f of f of f, and so on to infinity. So you can't actually extract anything out of this. So for the way I implemented this, for the way I implemented destructive rewrites, I just like simply do not permit removing that specific E node. And then another E node you can't remove is this one down here. Obviously, if you remove the last E node of an E class, you end up with an empty E class, and you can't really extract from an empty E class. So that's another rule that I implement, is that if an E node is the last member of its E class, you can't get rid of it. So those are the rules that we've for destructive rewrites. I tried implementing destructive rewrites in the math test suite for EGG and came up with some pretty promising results. So the baseline that we're comparing to has explanations disabled, first of all, because the way I implemented this doesn't work with the explanation system, and I'll cover that in a later slide. I also disabled pruning. So for the math test suite to complete on time in EGG, they use pruning in order to make sure that the egraphs don't get too big. So just as a fair comparison, I got rid of both pruning and explanations. And so we can have this nice little log graph here with the destructive rewrites on the y-axis and then the baseline on the x-axis. And you'll see that with the destructive rewrites, it does end up being much faster for a few of the tests, and then up to like a couple orders of magnitude faster for one of them. And then just for fun, I also compared this like with pruning, but still with explanations disabled, just to give it a fair shot. And you end up with some mixed results. So it basically shows that like pruning and destructive rewrites, they basically end up like as a wash when you compare them, which is nice because it means that my approach is sort of like doing something similar to pruning, where it's able to remove enough e-nodes and e-classes from the egraph to prevent the egraph from getting too large and slowing down equality saturation. In terms of next steps, one thing that is the two things that are really important for destructive rewrites are thinking about like when you want to destroy rewrites and what rewrites you want to get rid of. The way I implemented it is that it's sort of based on the backoff scheduler system. If any of the rewrites get applied too many times, then I get rid of that rewrite, and then I wait an exponentially longer time until I get rid of it again. But for which rewrites we want to get rid of, I'm currently just undoing every single rewrite, and that ends up being quite aggressive. So you want to think about, like, maybe you want to automatically identify explosive rules. For example, associativity, commutativity, any kind of rule where the left-hand side and the right-hand side have like the same cost, so it doesn't actually end up like improving the egraph in a greedy manner, are rules that you might want to consider. But it is like more complicated than that because with the example that I showed at the very beginning, it doesn't actually explode if you only have the associativity rewrite. It is the combination of the associativity rewrite and the multiply by 0 rewrite that results in the graph exploding. So there is a bit of subtlety here that is important to keep in mind. Another thing I've been working on is trying out destructive rewrites in Herbie, which is a really cool research project that uses egraphs for floating point optimization. So the accuracy of a floating point expression depends quite a bit on like how you arrange the operators in the expression. So rearranging them might result in much better floating point accuracy over like the range of possible floating point values. And Herbie uses egraphs internally for that optimization. So this is pretty nice for benchmarking. So I've been working with this. It's currently so slower than if you like ran like Herbie just like normally. But it is nice that it like does finish on time. It's not like much slower. So I think like with a few more strategies, like for example, like only undoing certain rules, this approach might actually work. And lastly, as I was talking before, support for explanations is also a work in progress. It turns out that the proof system in EGG is sort of like its own separate egraph. And one really interesting thing about the egraph that is used for the proof system, for the explanation system, is that it preserves history information. So for example, like which rewrite did an e-node originate from is a question that you can answer with the explanations egraph. So since that gives more information, that might end up being useful for destructive rewrites in terms of like making sure they're like more targeted and making sure that you're not trying to like remove too many parts of the egraph. Because as it stands, the EGG egraph doesn't have enough information, so the removal of e-nodes and e-classes is a bit coarse-grained. But yeah, so that's what I have so far for destructive rewrites. That's my URL for the slides. My fork is up there. And then I'll be starting the PhD at Northwestern in the fall. So that's not my UCLA email because I won't have access to it anymore. That's my Northwestern email. So if you would like to contact me, please reach out, and I'd welcome any questions. Thank you for listening.
Thanks for the great talk. We have plenty of time for questions. Great.
Thanks, really interesting talk. So we have something that's sort of in the same domain in Cranelift's egraphs, but almost a dual to this, which I find interesting. So if I understood right, your mechanism is basically that you match and then you say, okay, remove this specific thing. In Cranelift, we have this notion of a subsume operator where we say, here's the result of a rewrite, remove everything else, which we found to be sort of a nicer, more local way of thinking about things because sometimes we know that a rewrite really does get just the best possible answer. So like constant propagation, okay, if something goes to a constant, then we don't need any other expression. That's the best possible thing.
Yeah.
So I'm wondering if you've thought much about like when these different kinds of specifying destructiveness make sense, like what sorts of applications, and is one, are there use cases where they both make sense or something like that?
If I'm understanding correctly, that sounds kind of similar to like the pruning approach, where like because you know that an E-class represents a certain like constant value, you can kind of get rid of all the other E-nodes, and you're just left with the representative term. I think the way that destructive rewrites work can be adapted to work with that, because the way that pruning works in egg is that they kind of just toss out all the E-nodes, but it works for that because like it's not too, it's like pretty straightforward. It's just like all the E-nodes you're trying to remove like are in the same E-class. If you're trying to do something more complicated, you would have to start thinking about like the groundedness rules, the groundedness rule that I was talking about. So I think like for those situations where you have like more complex removal of stuff from the eGraph, it might be useful. That was like sort of like the biggest issue that I ran into when I was doing destructive rewrites, is that because the eGraph like so extensively shares information, it is really hard to like touch one part of the eGraph and only touch that part of the eGraph and not have like the house of cards fall down on top of you. So.
It makes a lot of sense. Thank you.
Thank you for the nice talk. So the destructive rewrites was not as fast as like Herbie normally running. But what about accuracy? Like, was it finding the same answers?
That's a great question. The accuracy was a little bit worse for some of them. It was actually a little bit better for some of them. I think on balance, the accuracy did end up being worse. Like, it wasn't finding as accurate expressions as it otherwise would have, because the eGraph kept getting like destructively rewritten. So I think that is an avenue to like look into. Like, why is the accuracy worse for some cases, but then why is it like better for some cases? So.
Just another question. Yeah. Do you like? So do you make like all the rewrites in Herbie's like rule set destructive, or did you choose which rules to make destructive, or have you tried like doing an ablation study, like which rules being destructive would change Herbie like by how much?
Yeah, so far I've only really tried it with like every single rewrite being destructive. I've tried restricting to specific rewrites. I'll need to experiment with that a little bit more, because like, for example, some of Herbie's rewrite rules are just like associativity, commutativity. Some of them are a bit more like multiply by 0, where it actually results in a lower cost term. So, but so far it's mainly been like making every single rewrite destructive.
So when you were talking about destructive rewrites, you had a bunch of rules for like when you wouldn't destroy a term, and those were all about like the structural validity of the eGraph, right? Whether it's like still an eGraph at the end. What about looking at cost information? You can imagine doing an extraction and never removing the cheapest node from an E-class or something like that.
Yeah, no, that'd be a really cool avenue for further exploration. I don't have time to talk about that here, but like taking in more information about the eGraph, as I said, right? Instead of just like thinking about the structure of the eGraph, thinking about like, oh, like if I remove this term, does that actually like, does this term actually contribute that much to the eGraph? Is a question that like my implementation doesn't answer at all. So thinking about like how useful is this term, and then maybe like thinking about the cost of specific terms would be really useful, because like the sort of intuition behind why you can remove E-nodes in E-class is that for associativity and commutativity, it'll add like a ton of like slightly different orderings to the eGraph, but then like maybe once you optimize, you rewrite those down to like a more optimized term, you kind of don't need what you had before. But as it stands right now, my implementation is very simple and does not think about that at all. So.
Okay, let's thank the speaker one more time.
Cool. Hello everyone. My name is Rupan Shusoi. I'm a CS PhD student at Stanford University. This is joint work with Benjamin Driscoll, Ki Wang, and my advisor, Alex Aiken. So this talk is called Incremental Equality Saturation, but what I'm really here to tell you is that you should stop throwing away your EGRAPHS. What do I mean by that? Well, if you look at the way many EGSAT projects are structured, it's roughly like this. The input term is inserted into an empty EGRAPH, EGSAT is run, and an optimized term is extracted. And this pipeline is run afresh for every term. This means that equalities that are discovered during EGSAT for one term are not retained while optimizing the next one. They must be rediscovered. If the terms we are optimizing are similar to each other, not sharing equalities across them means we are potentially leaving a lot of performance on the table. And indeed, we are not the first to make this observation. The Egg paper made essentially the same observation and introduced batched EGSAT as a way of obtaining this kind of sharing. In batched EGSAT, all terms are taken together. They're added to an empty EGRAPH, EGSAT is run, and optimized variants of each term are extracted. This results in significant improvement in performance as sharing between terms is discovered by the EGRAPH before any rewriting is done. But the central limitation of batched EGSAT is that it requires all terms to be available simultaneously. This is not true in any application with user interaction, as in any such application, there will be a delay as the user provides successive terms. Most compilers fall in this category. So the question is how to share equalities across terms that are only available at different points in time. One idea is to use the same EGRAPH for every term. Here's how that would work. We optimize the first term normally, but we persist the EGRAPH that is obtained at the end. Then, instead of adding the next term to an empty EGRAPH, we add it to the persisted EGRAPH, and so on. This also does not work, mainly because the current term is often disjoint with most of the EGRAPH. Let's see the problem in more detail. Say I have this big EGRAPH containing various terms and their equalities. Say the kth term I want to optimize is f of x. We insert f of x into this EGRAPH and obtain something like this. The problem is when we run EGSAT, the algorithm will try applying rewrites to the entire EGRAPH, when we only care about applying rewrites to two E-classes, the one containing f and the one containing x. The problem is exacerbated if the other E-classes are not already saturated, and I will discuss later that this is often the case. So to summarize, the central issue with utilizing standard or batched EGSAT for settings where terms are available at different points in time is that both algorithms lack a notion of current term. And this is exactly what incremental EGSAT provides. If you remember one thing from this talk, remember that incremental EGSAT extends standard EGSAT with the notion of current term, so that rewriting is focused on the part of the EGRAPH that is relevant to the current term. Let's look at the algorithm in more detail. We're going to consider a sequence or stream of terms, T0, T1, and so on, where we must accept each term, optimize it, and return the result before seeing the next one. The rest of the setup should be familiar. We have a rewrite set, a budget, which can be a maximum number of e-nodes to add, a number of iterations or a time limit, and a cost function, which is used to select the final optimized term. Let's look at a concrete example, an algebraic simplifier. We will consider a sequence of two functions of x. The first one is x to the power 0. The second one is the derivative with respect to x of x times 1. We have some algebraic rules. For example, the first one says that anything to the power of 0 is 1. The second says that the derivative of anything with respect to itself is 1, and so on. Our budget will be a maximum number of e-nodes, and our cost function will just be size. So we're going to try to minimize the size of our input terms. So we take the first term, we add it to an empty EGRAPH. This is what it looks like. We do standard EGSAT, and we obtain an EGRAPH like so. I flattened some e-nodes to simplify these diagrams. Note that we discovered that x to the power of 0 is 1. Next, we do the same thing for our second input term. We add it to an empty EGRAPH, run EGSAT, we get something like this. Note that the second x's E-class is the same as the previous term, but all these equalities had to be rediscovered by the algorithm. Now let's do the same example with incremental EGSAT. For that, I have to tell you about incremental EGRAPHs, which are the underlying data structure for our algorithm. An incremental EGRAPH is just a standard EGRAPH plus versions. There is a version for each E-class and a current or latest version, which is a global variable. There is an additional component that I will motivate in a few slides. Okay, we begin by setting a current version to 0. We add our first term to the incremental e-graph. It looks the same, except now every e-class has a version assigned to it. After incremental exat, we obtain the same set of equalities as before. Now, before adding the second term, we increment a global version to 1. After we add the term, we have something like this. Notice that the new e-class gets the latest version. The others remain at 0. And when we do incremental exat, the algorithm only applies rewrites to the part of the e-graph that is new. And at the end, we obtain something like this. No more rewrites can be applied at this point, since there are no e-classes left with the latest version. So I just mentioned that rewrites are only applied to the part of the e-graph that is new. Let's make that more concrete. If we have a rewrite rule with this left-hand side, then the rule in incremental exat is that the top symbol must match in an e-class with the latest version. And we impose no additional restrictions on pattern variables, except they form a valid e-match according to standard exat. There is one more restriction on e-matching that I will tell you in a few slides. Okay. So we saw how incremental exat uses versions to keep track of the current term and how versions integrate with e-matching. However, it turns out that versions alone are insufficient for making incremental exat practical. The problem is due to non-termination of exat. This unfortunately happens to be very common. Indeed, exat over all the rewrite sets we tried seem to be non-terminate. Non-termination, coupled with using the same incremental e-graph for optimizing many terms, leads to what we call the runaway e-class problem. To explain, consider a really big e-class containing hundreds or thousands of e-nodes. Say we order these e-nodes by cost. Consider a parent of this e-class which we want to rewrite. There are many, many candidates for rewriting. What happens in the runaway e-class problem is that exat squanders its entire budget rewriting terms that do not lead to a global or local optima, and the algorithm's ability to optimize severely deteriorates. How do we deal with this issue? Well, our insight was that f of E1, which is the lowest cost e-node in this e-class, is likely to be a much better candidate for rewriting than f of En, which is the highest cost e-node. And this is exactly the motivation for the second component of incremental e-graphs. It is a top K analysis. So if we go back to our big e-class from before, top K works by attaching an additional piece of information to it called the top K set. If we set K to 2, then we're going to track all e-nodes with the lowest and second lowest cost in this e-class. And K is equal to 2 is indeed the value we use in our experiments. With that, I can state for you now exactly how e-matching works in incremental exat. If you have a rewrite rule with the left-hand side like this, as before, the top symbol must match to an e-class with the latest version. And as before, there are no additional restrictions or inner pattern variables, but we impose a restriction on any inner symbols. If they match an old e-node E, then E must be in the top K set for its e-class. This restriction lets us focus our budget on terms that are likely to lead to a better final solution. Before moving on, I want to note that top K is largely orthogonal to incrementality, but it was required to deal with the runaway e-class problem. We could not obtain good performance of incremental exat without top K. And it could potentially be used in standard exat as well, although we have not tried it. Okay, now I'd like to step back and discuss some higher level properties of this algorithm. First, is incremental exat even sound? Well, incremental exat cannot find incorrect inequalities, as the set of equalities valid under incremental exat is just a subset of those valid under standard exat at any point. But it's also interesting to consider the relationship between the set of equalities found by the two algorithms. The general situation is best represented like this. There is a big intersection indicating that there is a large number of equalities that are found by both algorithms. Then there is a set of equalities that incremental finds that standard does not find. This is expected as incremental exat has access to more information. However, there is also a set of equalities that standard finds that incremental does not find. I want to explain why this is the case. Let me preface the discussion by reminding you that we're assuming that exat over a rewrite set does not terminate, which to the best of our knowledge happens to be the most common case in practice. Okay, so why might incremental exat miss equalities that standard exat is able to find? Consider a really big incremental E-graph that we have obtained after optimizing 100 terms. We increment our current version to 100. Now we have this new term, f of x, and we want to add it to this incremental E-graph so that we can optimize it. Well, to do that, I must pick a version for each E-class in this term. We basically have two choices. If I pick 100, that means I've chosen to activate both E-classes for rewriting. If I pick anything less than 100, then I've chosen to disable these E-classes for rewriting as per the semantics of E-matching. The problem is just that any time you choose to disable a subterm for rewriting, you might render an equality unreachable that is otherwise reachable by standard EGSAT. And you have to disable subterms for rewriting sometimes, because otherwise you're not getting anything from incrementality at all. So keeping in mind that no reasonable policy for picking versions can guarantee that incremental EGSAT finds every equality that standard EGSAT can find, our job with designing a policy is easier. It is just to obtain good performance. The policy we actually use in incremental EGSAT can be explained based on a well-exploredness heuristic. It says that every old E-class with at least m E-nodes is well explored, so don't explore it ever again. In practice, we set m equals 2. So let's see what our policy entails on the previous example. So we have this incremental E-graph, and we're inserting this new term into it. The policy just says that if the E-class that f goes into already has at least 2 E-nodes, then you don't do rewriting on it. And otherwise you do, and the same thing here. And this well-exploredness heuristic can also be used to explain the rule for merging of versions. So you have 2 E-classes, they have different versions, and you applied a rewrite rule that merges the two of them. In our design, we give the resultant E-class the lower version. And the rationale is just that, for example here, f is considered to be well explored after the merge because it is now equal to E-nodes that were already well explored. I want to stress that the design decisions we've made for incremental EGSAT, the well-exploredness heuristic, the rule for decrementing versions, only make sense when EGSAT is non-terminating. There exists an alternative design of incremental EGSAT that is suitable when EGSAT is terminating, that enjoys the property of always finding a superset of equalities of standard EGSAT. And in that design, versions would only increase, never decrease. And in that design, top k would be unnecessary as long as you always ran to saturation. However, we just couldn't find any rewrite sets for which EGSAT was terminating, and so this design was never implemented. Okay, with that, let's look at some performance results. After all, the whole point of incremental EGSAT is to improve performance. We'll use our running example, the algebraic simplifier. We randomly generate 1,000 functions of x of a given size. Our budget will be a maximum number of E-nodes to add. The cost function will try to remove derivatives and integrals while minimizing size. This is just taken from the math example in EGG, actually. And we will compare standard and incremental EGSAT in terms of total cost for the 1,000 extracted terms versus total time. Here are results for 1,000 terms of 2 different sizes, 11 and 13. Total cost is on the y-axis and total time on the x-axis. Each point here corresponds to a full run of 1,000 terms with a specific node limit. We see that as we increase the node limit, incremental EGSAT quickly becomes Pareto optimal over standard EGSAT in these two metrics. And for larger terms, we see that we need a larger budget before incremental EGSAT becomes Pareto optimal. Here are some detailed results for optimizing 1,000 terms of size 11 with a specific budget, in this case 6,400 E-nodes. Incremental EGSAT is about 3 times faster, and it finds solutions of lower overall cost. However, incremental EGSAT does not find an equivalent or better solution than standard EGSAT for every term. For the vast majority of terms, the two algorithms find a solution of equal cost. However, for 40 terms out of 1,000, standard EGSAT manages to find a better solution. This is just due to the problem we discussed earlier, where the sets of equalities the two algorithms find are not exactly the same. To conclude, I've presented a new algorithm for EGSAT that is able to reuse discovered equalities across terms that are temporally separated. The main limitation of the algorithm right now is its requirement of a local cost function. as that is required to even define what top k is. Non-local cost functions include, for example, if you want to solve an integer linear programming problem over the eGraph. Such cost functions are used in several projects, and relaxing this requirement is ongoing work. I'm also looking for more applications for incremental EGSAT, so if you have something in mind, please come say hi. Thanks for listening. This is the link to our abstract, and I'll be happy to answer any questions.
Thanks for the great talk. Okay, here we go. We have got some questions, and we have plenty of time for questions.
Hey, thanks for the great talk. This is Rajat from MIT Engine Street. So for your top K heuristic, this is probably not true, but is it equivalent to essentially pruning to the size that you select, or no?
It's not, because top K only kicks in when you have an E-class that is old. If you have, so if you take a new term and you start doing EGSAT on it, top K doesn't kick in at all. It's only when the new term shares something with an old term that top K kicks in, and it tells you, well, don't do rewriting on the old part because you probably already did it. And also, it's not equivalent to pruning in another sense, in that you can still get hash consent for E-nodes that are not top K. So if you have your E-class, it has some top K set. Consider some E-node that is not in the top K. You can still hash cons into that E-node, and that can still give you some share.
Thank you.
Yeah, thank you for the great talk. So just a simple, I guess, implementation question on top K. How are you determining the cost? Is it like you're running a cost function every time, or are you like propagating some data analysis throughout the eGraph? Yeah.
Yeah, so the good thing about local cost functions is that you can just implement them as an analysis. So it's just an analysis, basically.
Okay. Yeah, and I guess the future work is looking to getting a more global cost function there?
Yeah, I think for that you would need a local proxy to define top K, and then at the end you could do your global function, something like that.
Okay, cool, thank you.
Hey, thanks for the great talk. Yeah, one question about applications. So I was wondering, like, in my head, typically, equality iteration is kind of one input program that you want to optimize, like a compiler, and then you get one output. So you were thinking of a kind of a sequence of inputs that have some overlap. And I was wondering, like, what applications do you have in mind that have kind of this sequence as a typical input kind of?
Yeah, thanks for that question. Well, just think of a compiler, you know, you like write your program, you compile it, then you make some change to the program, then you want to compile it again, maybe you want to compile the program tomorrow. It's a sequence, like because you're running the compiler multiple times, and so the inputs naturally form a sequence. Like the only program that wouldn't have a sequence is a program that was only run once, you know.
Hi, thanks for the presentation. One question I had was, does the order in which you add the terms to the equality iteration matter? Do you have experimental data from this? As in, it's because you're kind of introducing a phase ordering in which terms get explored first, second, and I think later terms can benefit a lot from the earlier terms, whereas the earlier terms
Yeah, so this is true, but the model in which this is operating is that I don't have any control over the inputs I'm receiving. Like my perspective is that I am this optimizer, the user sends me terms, my job is to optimize them, so I don't really have an axis along which I can reorder terms.
Yes, sorry. The question was, have you tried playing around with switching up the order, and have you seen improvements or degradations in performance of the extracted terms?
So I don't have results for exactly the experiment you're suggesting. In this case, these terms are randomly generated. But I think if you do some pathological case where you switch around terms, you can get differences in performance, definitely. And in fact, for later terms, sometimes later terms will get saturated much more quickly because they have a lot of information already there.
Have you thought about how this would work with Eglog? Do you see any challenge for integrating versioning into Eglog?
So that's a great question. This implementation is just a fork of Egg, so this is not for Eglog. I think Eglog is going to have a lot of the same problems, like top K. If you want to do something like this for Eglog, you're going to have something like top K. because the runaway E-class problem where E-classes just like explode with useless E-nodes, that's going to occur. Versions, I think you could just implement straightforwardly. Some of the other details might be different. For example, this implementation has a special implementation of rebuilding, which is incremental. The standard implementation in Egg is not incremental. So I think that you would have to modify for this to work for Egglog.
Hey there, great talk. Thank you so much. I'm curious, along the lines of this question, if you've thought about how this relates to semi-naive evaluation and something like Datalog or Egglog. It seems like there could be some cool overlap there.
Right. So I think this is largely complementary to semi-naive evaluation. My understanding is semi-naive is just an optimization for E-matching. And in incremental EXAT, you basically only E-match over the part of the E-graph that is new. So like that's all, like I don't think you can optimize it further because like you have to match over the part that is new anyway. So my understanding is that this is complementary.
I have a question. I really do like this work because it's a very practical sort of motivation. You're willing to sacrifice completeness because we've already sacrificed it, right? It was never terminating to begin with. And we're sort of making these trade-offs of like, well, we'll give up a little bit of completeness there because it buys us more completeness in this direction because we now have more time space or whatever. And it seems like the main tool you're using here is this like very granular approach, which you both are using to get this top K and the incremental approach, which is like, we're no longer treating all members of the E-class the same, right? Yes. We're sort of discriminating between them, saying you can look at these, but not those at different times and so on. I think this is very powerful and probably a very necessary tool to like reach scalability, especially in this sort of incremental setting. But I also think that it sounds like we're opening Pandora's box, right? Like now we have so more knobs and knobs on knobs, and like you can imagine, you know, introducing, you're already bringing in sort of cost information to sort of steering the search. So I don't know, how do you sort of square that circle? How do you think about, you know, controlling the complexity of controlling the search?
Yeah, that's a great question. And this was like a major tension while I was doing this project. So before we had top K, like this would not work at all. Like performance was completely terrible. Basically what would happen is after you had optimized a few terms, the E-graph was like so big and full of like useless equalities that nothing would happen. You would, if you gave it a budget of like 5,000 E-nodes, it would just like create 5,000 useless E-nodes and finish. And so it's just that because EXAT is non-terminating, you have to have some sort of guidance to hope to get useful things out of really big E-graphs. And you need not be incremental. Like if you just think about doing one run of equality saturation, but with a humongous E-node limit, like the only way to get a benefit out of that is to have some guidance while you're doing it. Otherwise, like you will get the best thing in like the first 10% of the search, and the rest 90% will be like nothing.
Okay, let's thank the speaker one more time. Okay, this next talk was also someone who unfortunately could not make it due to travel circumstances, so we have a pre-recorded video, but the speaker will be on Discord live, so we can do live Q&A afterwards. All right, so yeah, just play whatever.
I'm Luke, working with my colleague Eric. We have built Outlog, an eGraph engine. It is notable in two ways. It is compatible with the subset of the Egglog language, and it's faster than Egglog the engine. We will return to Outlog shortly, but first, how are eGraphs actually implemented? eGraphs, when used for equality saturation, initially contain some E-nodes, here denoted by circles, and E-classes, here denoted by boxes. Over time, our rewrite rules add new E-nodes and E-classes to the eGraph. We also find that some E-classes are equal, here denoted with the dashed edges. Of course, equal E-classes are indistinguishable, so we can perform edge contractions, making the eGraph as a whole smaller. We have shown this process by drawing a graph, but the actual workflow involves writing a theory in a domain-specific language such as EGLOG, into which we can insert an expression, run a few steps of e-matching, and extract and simplify the expression. From an implementation perspective, this involves an eGraph data structure, which must support adding e-nodes and e-classes, merging e-classes, as well as searching the eGraph for specific patterns. This data structure is then used in alternating rounds of e-matching the rewrite rules and mutating the eGraph based on the matches, including performing e-class merging. Let's approach the implementation in steps. For e-classes, let's represent them as integers and use union find to implement merging. Then, since e-nodes, unlike e-classes, have a fixed degree in the graph representation, we can represent e-nodes as tuples with an operator-specific length. Our third implementation challenge is e-matching, which we can solve by recursively walking from the root of the pattern. We can filter e-nodes based on the e-class they belong to, as shown in the pseudocode, avoiding an exponential slowdown as we add more nodes to our pattern, or equivalently, more nested loops. Taking these ideas together, we very roughly get EGG, a very commonly used eGraph engine. It is relatively simple and easy to modify, but it is not the fastest eGraph engine on offer. EGG's performance is limited by its e-matching. The loop structure implementing this pattern, which appears in the distributive law, is suboptimal. If mul x has many iterations while mul y has 0, then placing the loops in this order is a serious mistake. Even more clearly, we don't use our knowledge of C1 while getting mul y, leading to unnecessary iterations. Both of these problems can be fixed with a different loop structure, with earlier checks and using all known variables wherever possible in lookups. There are many ways of arranging these nested loops to implement the pattern, and finding the best one is not obvious. A structured perspective on this problem is to view the query as a conjunctive join, turning the problem of finding a good loop structure into relational query planning. This allows us to apply worst-case optimal join algorithms, significantly improving upon top-down e-matching. Again, what did this actually mean? Our pattern trees can be turned into joins by naming the intermediate values, and we are no longer constrained to match the pattern from the root. We store our e-node tuples as rows in operator-specific tables. Joins combine rows from multiple relations based on having common values for specific columns. At this point, our eGraph is essentially a relational database, and we may look to that field for inspiration. Fast eGraph engines have to be fast database engines. Like how we filtered e-nodes by output e-class in top-down e-matching, our joins are not implemented as Cartesian products followed by filtering. Joins can be implemented using sorted data or with hash maps, finding rows with some known column values in logarithmic or constant time. Finally, our relational representation of rewrite patterns allow us to apply semi-naive evaluation, which essentially allows incremental e-matching. In the simpler naive evaluation, all results of an e-matching step will also be matched in all subsequent e-matching steps, which is especially inefficient when performing many steps on a large but only slowly growing eGraph. Semi-naive evaluation addresses this by splitting queries into many variants, each of which require one of their atoms to be among the recently added ones. While resulting in more queries, they match fewer times in total, making semi-naive evaluation a significant benefit overall. Implementing relational e-matching and semi-naive evaluation together, we would basically get EGLOG, and EGLOG is significantly faster than EGG. This wraps up our background on eGraph implementation, and we are ready to focus on OUTLOG itself. OUTLOG is architected as an ahead-of-time compiler, allowing new tricks based on whole theory preprocessing and optimizations between multiple rewrite rules. It is algorithmically similar to egglog, using relational e-matching with worst-case optimal joins and semi-naive evaluation. Concretely, outlog is a Rust proc macro, embedding an equality saturation theory into your application. It implements the core of the egglog language, including primitive types and merge expressions. And above all, outlog achieves significantly faster e-matching and rebuilding compared to egglog. Using outlog involves specifying an egglog theory in a proc macro invocation or in a separate file, during which compilation generates Rust code representing the theory. Although initial expressions and run commands can be specified in the egglog source, applications will reasonably prefer to feed it through the Rust API. This is especially efficient for large input expressions compared to generating large egglog files. Outlog supports both compilation in a strict mode, which is step-by-step compatible with egglog, and a relaxed mode, which finds more rewrites in every iteration and therefore matches egglog only after saturation. Finally, we would like to underscore how generating Rust code aids understanding, prototyping, and debugging outlog. You and me are already used to working with source code in general-purpose programming languages, and although the compiler part of outlog is at times messy, the generated code is more concrete and simpler than interpreter source code. Now, on to our benchmarks. As is evident from the abundant green on this slide, outlog achieves speedups over egglog across all benchmarks. The scenarios are math, which is taken from the egglog paper, Boolean adder, which performs rewrites on a 10-bit ripple carry adder, and fueled math, which is the math benchmark modified to prevent deeply nested integration by parts causing non-termination. As a disclaimer, note that this measures just the time spent building the eGraph and not extraction. The 13th step of the two combinatorially exploding benchmarks leads to out of memory on a machine with 128 gigabytes of memory. So outlog really does provide speedups across the entire range of reasonable input sizes, although especially for small eGraphs, where it is more efficiently using CPU cache while also avoiding egglog's startup overhead. You may notice that these figures look different from those we had in the extended abstract submitted 2 months ago. Outlog itself was something we began working on 5 months ago, so we have been able to pick a lot of low-hanging fruit, essentially even up until today. So why is outlog faster than egglog? One might think that compilers are just inherently faster than interpreters, but it is not that simple. We don't really know because we lack an expert understanding of egglog, but we can identify a combination of plausible factors. First, outlog both avoids interpreter overhead at runtime and sends along more specific code to LLVM, which is easier to compile compared to generic interpreter source code. Second, outlog uses indexes that are different from egglog. Outlog performs all index lookups in only a single hashmap lookup, although this requires more indexes and more memory for each. Egglog uses column-oriented lazy tries, which are conceptually nested hashmaps, sometimes requiring multiple lookups, although with the benefit of fewer indexes and less memory for each. Third, the ahead-of-time architecture allows novel optimizations that we will discuss shortly. Finally, we have spent a lot of time performance engineering outlog, which has led to a steady stream of incremental gains. The first of outlog's novel optimizations is try-query planning. This is based on the observation that theories with many rules often have overlapping query prefixes, motivating merging the for loops into a try. This transformation is performed at the same time as worst-case optimal query planning, and it is an example of how one can exploit the knowledge of all rewrite rules before starting to execute any of them. Second, Some rules provide permutation symmetries within single relations. In particular, there are often rules making operators such as addition and multiplication commutative. Inserting all permutations eagerly, whenever one is inserted, means permuting the columns leaves the relation invariant. This can be exploited for query planning. Many rules, including the distributive law, have symmetries. In this example, swapping x and y, as done by the invariant permutation, leaves the rule identical modulo variable renaming. This has consequences for semi-naive evaluation, in which we produce multiple variants of queries. In this example, the symmetry leads to one of the semi-naive variants matching a superset of another, meaning we can drop one, in some cases greatly reducing the cost of e-matching overall. Additionally, the invariant permutation means that some indexes would be equivalent, and as it can simply alias one for the other, Outlog avoids storing and maintaining both. While we have focused on Outlog's strengths, there are also limitations. Outlog fails much of the egglog test suite due to missing features such as rule sets and containers. There is nothing conceptually or architecturally preventing Outlog from implementing these, but we have simply prioritized the performance of the core language. Other features, such as extraction, are available only through the Rust API, not through the egglog code, to suit the embedded rather than interactive use case. Outlog, as an ahead-of-time compiler, has different priorities from egglog as an interpreter, with many second compile times making it more suitable for applications with a fixed set of rewrite rules, rather than with dynamic ones or in REPLs. Finally, Outlog's tree extraction is not optimized or benchmarked, as we have up to this point focused on eGraph building. A reasonable question to ask is to what extent Outlog's ideas can be implemented in egglog proper. While this is in principle largely possible, there are two hurdles. The first is that this requires whole rule set query planning and optimization, possibly interfering with the ability to add and run rewrite rules in an ad hoc manner. Secondly, and perhaps on a more fundamental level, doing optimizations requires relaxed semantics. One example of this is egglog's non-deterministic mode, which allows building eGraphs that are correct only after E-class ID renaming. Outlog's strict mode inherits this same relaxation, additionally not guaranteeing anything about the order in which rules are matched in a single step. This relaxation is typically observable only in the presence of a merge expression, which is not part of a mathematical semilattice. Finally, the invariant permutation optimizations effectively execute the commutativity rewrite eagerly, triggering e-matches earlier. This causes even the number of e-nodes in the eGraph to diverge from egglog, up until saturation, where the eGraph again is uniquely determined, modulo the previously discussed relaxations. As the eGraph only matches egglog upon saturation, invariant permutations are only enabled in Outlog's relaxed mode. This brings us to the end of our presentation. Outlog itself is accessible on GitHub at the following link. We built Outlog as our master's thesis, which is titled Outlog, a high-performance eGraph engine, and will be published soon.
Okay, great.
Hello.
Yeah, hello, we can hear you.
Yes, perfect.
Thank you for the great presentation. Hopefully we have some questions from the audience. Okay, here we are.
Hi there. That was a really awesome talk. Thank you. I'm wondering about a situation where I know some of the rules that are fixed ahead of time and some of them are dynamic. And I'm curious if you have any thoughts where maybe we could like compile that initial set of rules and then switch to something like egglog dynamically later.
So, like, it's entirely possible. It's engineering effort. I think the largest issue with that is that we decide what indexes to keep statically. Although that decision is very simple, given that we don't use tri-indices, we use flat indices. So like, it means writing a bunch of extra code in Outlog, the source code in the compiler to support that, but it's in principle nothing preventing it.
I have a quick question while I make over to the next question asker. As you stated in your slides, an eGraph engine, especially a sort of egglog style eGraph engine, is of course a database, and you've implemented a high performance one. And so that maybe naturally begs the question, have you considered comparing against other just data log engines? There are other, code generation is a pretty relatively more standard technique over there in database world. And so that could be a interesting way to do sort of apples for apples comparison. Is this something you've looked at?
So we have not.
Well, a tiny bit, and like the main difference is that for data log engines, you never remove anything. So like fundamentally, you can have like the indices always grow. So then you like really simplify your problem.
Yes. And then in terms of the problem is really quite similar. Then we're doing very similar things. We just haven't compared against the concrete things. It's also a question of like all of our benchmarks are written in egglog. So it's super convenient for us to compare against egglog and inconvenient to compare against anything else.
Thanks. We have some more questions over here.
This is not quite a question, but we would love to test out Outlog in Herbie. I think it would be a lot of fun, and we have a version that works on egglog, so it probably wouldn't be that difficult. And for others, we have hosted some prior eGraph optimization projects, and we'd be happy to host more. So if you want to test your eGraph engine or similar on Herbie, DM me. I would love to get you involved.
Yes, you're the one who wrote in the chat, right? Yeah, I'm taking that as a yes.
Hello. So this is very exciting work. So one thing I'm wondering is, it seems like your framework, because like in egglog, like one big headache is how you can have interactions with functions written in Rust, because like egglog is an interpreter engine, like everything is boxed, have their own like value type. I can imagine like your framework will be more flexible to these functions written in Rust, because you're basically just generating code, and this can be used by others writing Rust functions.
Yeah, absolutely. It's again an engineering effort, but it's just like we want to make the line go up, and then we focus on performance and the benchmarks. But like those sorts of features are totally reasonable to add.
The other question I have is, I may miss this during the talk, but are you using like hash join for your join algorithm?
Yes, all the joins are hash joins.
Do you think maybe like some of the speedups is from by using a hash join algorithm, which are a smaller constant factor if you are dealing with simple joins, simple queries?
I mean, egglog also uses hash tables. It's again, we don't know like all of the details of egglog, but egglog to us is like textbook generic join, while I guess we do something which is kind of free join, although we didn't realize that at the time. Yeah, like so the fact that we can do one index lookup for a task that requires 2 or 3 for egglog is a factor. Finally, as a side note, we are not convinced that like we would want to do hash joins. We would maybe want to do like SIMD and just having things sorted in the right direction, but hash joins are quite simple. So,
thanks.
Yeah.
Great talk. CodeGen's super fun. Yeah, so I feel like your approach is probably going to be harder to use from other languages other than Rust, which is like one thing that egglog offers as an interpreter. It's like easier to ship a binary that you can just make bindings to in other languages. So I wondered if you have thoughts about like how you might go about doing that part, like if you want to have a Python interface,
Like if you write a compiler and know everything in advance, like if you have a specific set of rewrite rules and like schema, you can specify that in Rust and have some like translation layer into your Python. But like you have to like maintain your like Rust layer.
Or like presumably we could probably generate that thing. Like the fundamental restriction is that it's non-trivial to add and like it's non-trivial to add new rewrite rules at runtime, and like never mind adding new tables and stuff at runtime. But like Python bindings would be fine, probably. Just the fact that you can't do it, you would need to compile some code between changing your rewrite rules and running your thing.
Gotcha. You can't generate rules in the Python bindings, yeah.
Okay.
Where the Python bindings would need to run cargo in the background or some annoying thing.
Let's thank the speakers one more time. Okay, and with that I think we resume here at 3:40. Okay, folks, welcome back for the final session. Again, we're going to wrap up a little bit early here, so we have some time for plenty of questions and discussions. We've got 2 talks on sort of related topics here, and then Phil is going to close us out with something completely different. So yeah, when you're ready, please take it away.
Yeah, thank you. Check. Okay, great. So hi, everyone. My name is Rui, and welcome to the session of theories and guidance. So I know it can be a little bit weird, but I would like to emphasize this session's name because this is the only connection between this talk and the series. Yeah, and next I'm going to talk about large language model, which would be a complete opposite of series and maybe science, right? Yeah, okay, so seriously, the main topic of this talk is about our recent attempt to guide equality saturation with large language models, and mainly about how we discover and fight against the limitations of the current large language models. Okay, so at the very beginning, this work is motivated by the recent huge success of large language models for program optimization. They have been reported to be able to success CUDA kernels, fix practical performance bugs, and optimize complex algorithms for competitive programming. Yeah, and in these tasks, the key advantage of large language models is their rich knowledge obtained from the large-scale pre-training so that they can easily scale up to complex programs and offer large-scale optimizations. Yeah, but on the other side, no matter how impressive these results are, large language models always suffer from the risk of generating incorrect optimizations. Yeah, and recently, as the large language model becomes more and more powerful, this issue has become more and more tricky because large language models have become better to generate plausible but actually incorrect programs. For example, in the work of CUDA optimization, they reported that their agent is so clever that can utilize a memory exploit in their evaluation script, so that sometimes it will hack it, use an incorrect program, and make the tool report a false speed up, which can be as high as 100 speed ups. Okay, so this is the current stage of large language models, scalable but unsound. And I believe such kind of situation can easily remind us of those traditional techniques, right? Program rewrites, equality saturation, EGRAPHS, because all of these techniques are sound by construction but suffers from limited scalability. So in this work, we aim to answer this question, that is, whether it is possible to combine these 2 approaches and keep both advantage, and in this way to get a program rewriter or optimizer that is not only scalable but also ensures the correctness. Okay, so this is a very natural and straightforward idea, but there's still some huge challenges prevent us from getting such a good combination. So the major challenge comes from the gap between practical rewrite systems and the current stage of large language models. So from one side, current practical rewrite systems have become very complex, so it is very difficult to teach large language model to use such kind of rewrite systems. For example, some practical system can comprise hundreds of customized rewrite rules implemented in thousands of lines of code, and moreover, this code will closely entangled with many external components, such as customized DSL or some external solvers. But in contrast, the current learning ability, especially in-context learning ability of large language models, is still limited. In most cases, they can only capture a very few amount of information in the prompt, which is far from sufficient to grasp the rewrite system. Yeah, and from the other side, from the output side, even if we assume the large language model can understand the whole rewrite system, it is still fundamentally challenging for it to output the correct rewrite chain, because large language model is trained mainly over a pretty high-level descriptions, high-level ideas, but rewrite system usually work on a very, very low level. Let us consider a very simple problem. We call it freshman string. Its goal is to prove that the square of x plus y is equal to the square of x plus the square of y. So clearly this is wrong, but it is true under a very specialized rule that if we assume every expression plus itself will always be 0. Then for this task is very simple and can be easily described within 100 tokens. But even one of the current best large language models cannot solve it correctly, because in some intermediate step, it will forget to maintain the low-level structures and will incorrectly use the plus operator for different inputs, which is incorrect. Yeah, and such kind of details missing problem will become more and more significant in practice because usually we will need many different rewrite steps comprising many, many different tokens. So it would be a mission impossible for a large language model to keep track of all of these details correctly. Okay, so this is a challenge, and now the problem boils down to how to bridge the gap between large language models and rewrite systems, right? So our solution comes from, it's mainly motivated by this previous work, guided equality saturation. So their key insight is that they find human users are very powerful. They can find useful checkpoints in the rewrite chain, even without knowing all the details. So for example, for the previous task, before going into details, we can easily come up with a roadmap of how to rewrite from the left turn to the right turn, right? So we will know that we should first try to expand the square operator and unfold this multiplication into some low-level sum. And at last, so we need to somehow cancel out this duplicated term x times y. Yeah, so such kind of roadmaps can provide a very strong guidance for equality saturation because we no longer need to rewrite directly from the left to the target expression. Instead, we only need to consider the rewrite from each checkpoint to the next, so that we decompose the whole task into many much simpler subtasks. Then the scalability can be improved significantly. Okay, so we can easily generalize this idea to our case, right? Because large language model have exposed human-like capabilities in many different tasks. So a natural idea is to use large language model to take the charge of human developers to provide a high-level guidance to equality saturation. In more detail, so given that large language model cannot handle all the low-level details, we can just put it at a high level and provide it only with the task description. And instead, for these low-level things, for example, concrete programs and the detailed rewrite system, we still use the traditional techniques to keep track of it. So in each round, we will first run equality saturation. We run program rewrite with a moderate resource limit. And the only goal of such kind of rewrite is to move through enough low-level details to reach the next checkpoint. It means that we expect this intermediate EGRAPH will contain a meaningful checkpoint for the current rewrite process. And then the remaining problem is how to extract out the checkpoint from this intermediate EGRAPH. So to do this, we will put a query between these two different levels. This query takes the whole EGRAPH and raises high-level queries to the large language model and takes the response and uses this response to pick a checkpoint from the EGRAPH. And once such a checkpoint is decided, the low-level process will move to the next round. We will run rewrite or equality saturation again to move to the next checkpoint and then run the queries again. So this process will repeat and repeat until we find an expected result or this whole process converge. Okay, so this is the high-level workflow of how large language model guided equality saturation works. And here, the key idea is to use a query to hide all low-level details from the large language model. And of course, clearly, the performance of such kind of framework highly depends on how we design this query. Actually, this design choice is very tricky and suffers from a very tough trade-offs. The first challenge, the first side comes from the large scale of the EGRAPH. Right? We know that EGRAPH can be very large after even a few rounds of equality saturation, and there can be exponential number of programs in the EGRAPH. So it means that we cannot use some very simple queries, like for each program, ask the large language model that whether this program is good, or whether the next program is good, or whether the third program is good, right? Because we do not have enough time to traverse the whole EGRAPH. So this challenge will push us towards the direction to use some more informative queries to get more information in each interaction. But then at this time, we will meet the next side, the next challenge. That is different from human users. Large language model is not very reliable, given that here it takes only high-level descriptions instead of any low-level details. So for example, if we ask it to directly output a checkpoint, then with a high probability, it will give us a very wrong program. For example, it can be syntactically wrong or can even be not equivalent. So to design a good query, we need to find a very delicate trade-off between these two sides. And actually, to be honest, I don't think we have totally solved this problem. So what we have done is to try and evaluate several different design choices. And here, I will show you the current best solution we have ever found. OK, so our current design combines a query method and an error correction model. It will run in several steps. So in the first step, the first query is very close to the direct query, but it focuses on subprograms. So this query will first ask the large language model to focus on a subprogram and then provide a checkpoint by modifying only this subprogram. Yeah, but of course, large language model is also allowed to change the whole program. So the main effect of this query is to make it as much focus on subprograms as possible, because it will reduce the scale of new expressions written by the large language model, which means that the total noise introduced will be reduced. Yeah, and even though with a high probability the result can still be wrong, so we will try to correct these errors during the extraction. So we will use a customized extractor that try to find a program from the EGRAPH and minimize the string edit distance from the program and the raw output of the large language model. And such kind of extraction can be done efficiently by dynamic programming. And at last, because such kind of extraction may change the program, so we will have a final check with the large language model whether this program is equivalent or actually or better than the checkpoint you suggested. Back to the previous example. So our query will be like this. So first, we will ask for a checkpoint from the initial expression to the target expression. And then large language model will provide us with a wrong expression. And more worse, this expression is too far away from the initial expression, so there is no equivalent form in the current EGRAPH. So at this time, the extractor will come up with a very different expression with a very large distance. So with no doubt, it will be rejected by the model in the final check phase. Now how to fix this? So such fail means that the current checkpoint is too far away from the initial expression. What we need is a closer checkpoint. So we will restart a new round of query by asking for a checkpoint from the initial expression to the previous checkpoint. And then at this time, the output will be much more reasonable and much closer to the initial expression, and then the extraction will work well, and this expression will be accepted by the large language model. By repeating this procedure, we can solve the freshman stream problem with a very tough resource limit, where we only allow 3 iterations for each round of saturation. So this is the whole procedure. So after the first round, in the second round, the model will still choose to modify the whole expression, and it wants us to expand the whole multiplication. Yeah, and here during the extraction, we will supply the low-level details to make it correct. And then in the next 2 iterations, the model will focus on the subprograms and try to reorganize these subprograms closer to the target. And after that, the last checkpoint will be close enough to the final target, and then we will move to it in the last round of equality saturation. OK, so this is everything about our current approach. And because this is only an ongoing project, so we only have some preliminary evaluation on it. So what we have done is we tried to reproduce the case studies in the work of guided equality saturation, especially the case study on the Lian proof generation. So in the previous work, they built a tool chain that can convert Lian theorems to a rewrite task, where the theorem will become a goal and all available lemmas will become rewrite rules. And they show that with the guidance from the human user, equality saturation can prove some non-trivial theorems. And what we have done is to reproduce all of these case studies by replacing human with large language models and with a very high-level task description provided. So it means that at least in these cases, large language model can provide human-level guidance to the program rewrite. Yeah, and the theorems we have proved covers group theory and the freshman stream task we have seen, and one of its generalized version, and also the proof of the binomial theorem. And among them, I would like to expand a little on the task in group theory, which is pretty interesting. The goal of this task is to prove that the inversion of A times B is equal to the multiplication of the inversion of B and the inversion of A. And the key point of this proof is try to expand the original term by unfolding the identity element into expressions. For example, unfolding 1 to A times A inversed. And by repeating this procedure twice, we will be able to cancel out the original term and get the final term. But we know that generating such kind of rewrite is pretty tricky in equality situation, because it will involve an expansion rule with free variable on the right side. And to support such kind of rules, one pretty complete way is try to use a customized applier to let this free variable to match all possible E-classes. But it suffers from a very significant efficiency issue because it will double the size of the E-graph in each application. Yeah, but what we have found is that such kind of solution is pretty good under the guidance of large language model. So the key observation is that it is not so common to apply such kind of expansion rule in rewrite, which means that once we have to apply it, it will represent some important tricks in the proof, which must be captured by the high-level roadmap or be recognized by the large language model. So with this observation, we can handle such kind of expansion rules in this way. So we can, in each round of rewrite or in each round of equality saturation, we can first run without the expansion rule. And at this time, the proof will start before the trick. And then we can just apply the rules just once and to let the proof chain move over the trick. And in this way, the trick result will be included in the E-graph and then can be extracted out or be found by the guidance. Okay, so this is everything we have done and in the future. Yeah, as you can see, our current work are mainly worked on very simple rewrite systems, which is a little bit different from our motivation. So currently, we are trying to apply our current approach to some more practical rewrite systems, including the Stalinski's rewrite system and the rewrite system for the right DSL. The first is for synthesizing structured CD models, and the second is for optimizing tensor-related or array-related programs. And here, there will be many extra challenges. For example, the definition of this rewrite system will be much more complicated, and they will involve customized DSLs, and also this code, their code will entangled with many external components, such as solvers, type systems, and many heuristics. Yes, actually, we don't really believe that our current approach can be generalized to such difficult tasks, but it is interesting to explore how to make it work. At least we have some good news that large language models are actually very good at understanding new DSLs, which we thought could be a challenge before. So for example, in the case of Stalinsky, this is a very complicated DSL program extracted from the left side model. And this DSL is pretty new for the large language model. But what will happen is we only need to throw this whole program to O4 Mini and only hint it that this program describes a CD model. It can perfectly recover what happens in the original model. So its output says that it is a rectangular box with slots, and there's also a shallow backing box on the other side. Yeah, so it means that actually there's some magic in there's indeed some magic in the large language model and can provide some guidance. The only question is how can we extract it out to get the equality saturation. Okay, so this is everything about my presentation, and this is a simple summary. So our motivation is to try to combine these two complementary approaches, large language model and rewrite systems, to make it not only scalable, but also ensure the correctness. And our key approach is to introduce a query to hide all details from the large language model. Yeah, thank you very much. Oh, and at last, I would like to, at last, I would like to thank the authors of Guided Equality Saturation, especially Thomas, because he really provided us much help to this project. Yeah, thank you.
Thanks for the great talk. Do we have questions from the audience? Okay, great.
Hi, thanks for the great talk. You mentioned in the beginning that the LLM has problems because it's trained on high-level ideas and the context length is not sufficient.
Yep.
I wonder if you could try fine-tuning a small to moderate size language model on something like this, and whether fine-tuning would be like a good strategy to do it.
Yes, that's a very good question. So we do not choose to do so have many different reasons. So the first reason that we do not have enough resource to fine-tune a large language model. And more importantly, for me, I think I want to leave fine-tuning as a last weapon, because fine-tuning will introduce too much different factors and too much reasons to make our work, to make our approach works or not work, right? It depends on how we fine-tune the model and how we prepare the training set and many different other things. So far what we want to do is to check whether large language model can work before introducing fine-tuning. And on the other side, fine-tuning should be complementary to the current approach, right? Because I don't think fine-tuning can solve everything. So what it can do is to improve the accuracy of the performance of the large language model, but with such kind of guidance, it will work better. Yeah, thank you.
Thank you for the the great talk. You kind of hinted at it, I think, in the last part with the proof of A, B inverse is equal to, and then the times one, and being able to split up the times one. So if I understood correct, the LLM is basically, you're kind of using the LLM to find out when you want to actually turn this rewrite on, because it's like, it just blows up your graph in every other stage, and it's only useful here. So I guess that kind of leads me to my question of like, have you thought about using the LM to like select which rewrites you want in each stage? Kind of like a more advanced version of this, where you're like, this is the checkpoint here. We need to get to another checkpoint. What rewrites should we continue with? As opposed to just the complete set.
Oh, that's a great question. So yeah, I think large language model can provide many different kinds of guidance, right? So here we just follow guided quality saturation to provide checkpoints. But of course, so its key advantage is that it can understand what should happen during the rewrite. So of course, it can know which kind of rewrite rules should be applied at which stage. But here, I think a key limitation of large language model is that it is too expensive, so we cannot invoke it many times. So for example, if we expect to, in each round of equality saturation, to query the large language model to select which rule to be supplied, then its cost will be too high and we cannot afford it. So there should be a trade-off, but definitely such kind of guidance will work. Yeah, thank you.
I'm going to abuse my power to ask a question that sort of is very related to that, about a sort of alternative form of guidance. For this example that you have here with the group inverse, it turns out that you don't actually need the reverse inverse rule that like expands into 1 over 1 goes to x times x inverse, if you just happened to have A times A inverse just already there in the eGraph, right? This was mentioned in an earlier talk, these demanded, these like magical terms that if they just happened to be there, right, the proof would just go through with, in this case, a more limited set of rewrites. I guess my question is that, do you think that would be something that would, I guess, generalize to the applications that you're interested in? A form of guidance where it's not necessarily use this rule, but just, hey, give me a guide term that we're just going to put in the eGraph. We're not even going to equate it to anything. We're just going to say, we think this might be an important term to think about.
Yes, that's a great question. So I think from a high level, the answer is the same, right? We can expect large language model to provide guidance in any forms. But according to our experience, so large language model cannot do some pretty abstract thing. So what is abstract? For example, writing a sketch is pretty abstract. And another example is that writing a potentially useful term is pretty abstract, because it cannot know why this term is useful for equality saturation, right? So because it cannot understand the very details in eGraph or the AI library. So it may not work, I guess, but it is worth trying. So yeah, thank you.
Yeah, thanks for this very interesting talk. So I'm also staying on this slide, and I wanted to ask a question about this magical term as well. So if you go to basically every other lecture
first year lecture on group theory, you will have this proof, right? So it's very likely that the data set of where you trained the LLM had this concrete proof and this concrete example.
Yes.
So do you think this will work for things that the LLM hasn't seen before, maybe, or do you think this is so will it generalize for other kinds of things? Have you tested it on other?
Yes,
stuff?
that's a great question. So as a conclusion, so we haven't tested large language model on other tasks it could, it cannot see because it's pretty challenging to construct some data set that large language model have never seen before. So for the data leak problem, so maybe 1 year ago, my opinion is that large language model can only solve the problem it have seen before. But now I think my opinion is that maybe such kind of tricks is finite in this world. Or for example, maybe 100 tricks can solve 99% of problems. So it would already be great if large language model can memorize all of these tricks and can somehow generalize it to similar scenarios. Yeah, but we will test more on these observations in the future.
Yeah, cool. Thanks.
Okay, let's thank the speaker one more time.
Okay. Is it there? Okay. Now something absolutely different and totally unrelated. Machine learning guided equality iteration. We drew sticks and I lost, so I go second. What I want to present today is also related to scalability challenges of equality iteration. And here I start with the classic problem. We want to prove equality between two different terms. We have the start term and the goal term. And then we run the equality iteration, or at least we want to run it, but, well, the world catches fire and we run out of memory. And this challenge has been recognized by this guided equality iteration paper, which was just mentioned by Thomas Köhler and et al. And what I found in their research was that for relatively simple goals, like this is related to tiling a loop or matrix multiplication, that, well, even very simple operations take very, very long, consume a lot of RAM, and as you can see here, can generate a lot of data. And that also relates to that most of these are even unsolvable on like very relatively beefy machines in a reasonable amount of time. So what they came up in their work was having a guided equality iteration where we introduced these guides, as was previously mentioned, provided by human experts so that we don't have the huge problem to solve, but we try to go in tiny steps that are each feasible until we reach the end to have a better chance at solving the whole thing. So what are these guides? And I want to go a bit more in detail. And these intermediate goals or guides lie along the rewrite path of the whole problem. At least that's where they're supposed to lie. So they can be either some concrete term that say, hey, this term I want to prove now, then this one, or they can be kind of sketchy with holes. So this one here would be a concrete term. If you have like a map a loopy program, and everything is concrete. But then we can turn it into a sketch by introducing question marks, where we say, I don't really care what's in there, but I want to do equality situation until I have something that's kind of this shape in the eGraph, and then extract that and move on with the next step. And this also allows the author of the sketch to be much more imprecise in their sketch and give more leeway to the equality situation itself. So this is expert-guided equality situation, but you can see in the middle there's like a human, and let's get rid of the human, because we have the problem, these sketches, writing those, it takes a lot of time. It's not very easy, and it's not very beginner-friendly, and you need domain knowledge about what problem you're trying to optimize, because maybe you have a Zelinsky compiler, as mentioned, that's more about like reshaping a geometrical problem, or a loopy program, or we've heard about like biochemistry today, so, or chemistry, all not things that are easy to pick up in an afternoon. So what we propose is machine learning guided equalization, where we take the human and replace it with a machine. So yeah, I've heard you have to have sparkles nowadays for this. So yeah, we replace the human with a machine learning model that generates, based on the start and goal term, these guides instead of the human. So let's think about what the model should do. Well, it should generate as a suitable sketch. Well, great. Ideally based on the start and end goal term. So what do we need from the model? Of course, generate guides. That's why you're here. It can deal with terms, and that's very interesting because terms are not inherently like flat text as you would expect from a large language model, but they have a tree structure. They also should be somewhat performant because we don't want to run like a cluster of a supercomputer for solving relatively simple problems. And hopefully it builds on pre-existing work because we don't want to reinvent everything. So when we go to the shopping list, with this shopping list to the zoo of ML, what can we pick? Well, we could go with classic ML, like there are decision trees, Bayesian learning, all these, well, classical things, and of course neural network and deep neural networks. And since deep neural networks are especially like proven to be able to generate complex structures, including images, graphs, and of course text, we went the route of neural networks. But then again, now you've gone down one branch, but there are many options to choose again. So we could go with an LLM, and that has the advantage, well, it's readily available, but it only processes everything as a linear sequence of text. Like we've seen, we put in S expressions, and we have lots of brackets in them. We also have the problem this discards completely the AST structure and needs to recover it by interpreting the S expression itself. Training one, yeah, at home is also, at least for most people, prohibitively expensive. Even fine-tuning one can be very costly, computationally speaking. But lots of performance engineering has gone into making it fast, and we would like to have that. And it obviously can produce things. On the other hand, we have like graph neural networks when we go the other route and say, hey, we want something to take advantage of the structure. These work on general graphs. They can use the AST structure to some degree. They can be more economical when they're like smaller and more dedicated to the problem. But less work has gone into optimizing these things. And also the generational capacity is somewhat limited, I'd say. So what we've done is come up with something that lives in the middle, what we call a tree transformer, building on prior work, that works on trees, uses the AST structure, should be economically to run, but uses some performant components from existing transformer and LLM architectures, and also has a similar generational capacity. So we call it a tree transformer, and here's the pretty picture for it. I'm certain everyone understands it, and I have to explain nothing. So no. So this general structure of this is a decoder with a transformer decoder with self-attention and 2 cross-attention layers. So I mentioned in the start that we want our model to generate guides based on a start and a goal. So these are for us two different inputs we want to give the model. So we have at the left and the right, but they both take the start and the goal term and feed those into the autoregressive decoder on the left side. And these two cross-attention layers pay attention to what's being given from the two encoders. So we generate each node of the AST of our guide node by node. And this also has the advantage that we never have to care about being syntactically correct because we directly generate the tree. We generate the partial tree, we feed it back in, and autoregressively we can generate the whole tree. So here is how this works. We have at the start, then we add a node, then this creates two nodes, and so on. So in addition to this, we also use a tree-specific attention because textbook attention, like something like rope attention, only encodes the linear distance between two different positions. But what we use is something called disentangled attention that gives us the option to encode additional positional encoding in the model. This allows us to include ancestor-child relationship of the tree in the model, but also sibling-to-sibling order between different nodes. So now that we have a model, we also need training data to feed this whole thing and even train it. So we want these triples of start, guide, and target, but there's no large pre-existing data set for most problems that we want to tackle. We're dealing with languages that have very, very few users, so we need to generate the training data ourselves. And here we can use equality saturation to generate training data for later to use it for equality saturation, which I think is nice. So we seed an eGraph with an initial term from the language. And what we do then is we grow the eGraph by applying rewrite roots as in a standard equality saturation. And at some point, we reach a limit of the size of our eGraphs, and we start extracting from one E-class term pairs, where we take an E-class and we pick two random terms. And we do this multiple times. From that, we get the explanation between the equivalence between these two terms. And this sequence of rewrites we can slice up into nice triples, where we take the middle as the guide, and we have the left and the right as the start and the goal. And from that, we can generate training data quite easily. So I now come to the implementation and training. All of this is done on the RISE language, and we have about 8 million training tuples we're working with, which of course we can scale this up pretty easily. It's very easy to parallelize because once we have the eGraph, we can throw it on many machines if we want to, and just sample more or do this process with different seed terms. The model is also relatively small, meaning for a large language model size, it's really small. And we can train it like in 2 days or even less on a consumer GPU, which is very nice to iterate and also to run it later in inference, which makes it smaller. So what we see is that the structure matches for the higher levels. So these are, for example, two ASTs that we have here. On the left side, we have the ground truth of the guide, and on the right side, we have the generated one. So we have, under higher things, we have like smaller mistakes still. And again, we are in a relatively small model yet. And here's something, we have an additional node that's generated here, but as we go down, we lose, so these two are completely different because we have a let that's swapped with an app, and from there, the generation breaks down. But what we think and what we aim to do is like, this shouldn't be that big of a problem because we can reintroduce sketchiness because we have access to the output probabilities of the network. Meaning, if the network becomes uncertain about generating the next token, we can continue, but we can remember that and later replace this subtree of the tree with a sketch or a hole. So, So for the next steps we want to go to, we have this working prototype model. We can generate these guides from start and end terms in the RISE language. We want to scale to larger jumps. At the moment, we only have a relatively small rewrite distance between the two jumps. We are looking for metrics for how good our generated guides are, which is important for our evaluation. Then we can actually start evaluating these guides beyond just pure similarity to the guide, because even if the model generates something else than the ground truth guide, it could still be a very useful guide, and we would be very happy with that. So, and you can find the code and parts of the data set. It gets updated quite often. Check it out, and thank you for listening.
Thanks for the great talk. I'll start us off with a question. I was very interested to see that for generating the training data, from a single proof trace, you generate a bunch of triples, sort of regardless of where the, I guess, the intermediate term appears in that rewrite sequence. Was this like, obviously, you know, you want a lot of training data. This is the way to get the most. Do you have any like sense in terms of like how valuable a particular tuple is to have in the training set, right? Like, yeah.
No, we don't. And at the moment, we have not run into the issue that we have too much training data and we need to filter down. But that's certainly an option we might look into to prioritize those that are the most novel or that provide some insight. But at the moment, we try to use what we can and hope everything contains at least a little bit of insight and improvement. But that's certainly an option we can look into. Yes, thank you.
I have one more question for the, oh, wait, okay.
This is really cool, fantastic talk. Maybe building on Max's first question. Sorry, Max, I'm being a bully. So when you extract the proof, Egg makes a effort to find like the shortest proof. Like if you had magically run the rules in just the right order, this is what you would have gotten. And I wonder to what degree that means the targets you're looking at are sort of trying to find like fast forwarding patterns or like rule fusions that allow you to skip a lot of intermediate steps. Does that make sense? Or?
Yeah, yeah.
And I was trying to figure out the way that relates to the way I understand sketches, like in the earlier, like Thomas's earlier work in RISE and Michelle and everybody, you know, the whole group, being used often more like trying to find, you know, get to a normal form or something related to like the cost function where I happen to know this shape of program is going to be very efficient. And so I guess I don't quite understand if there's a connection between this kind of fast forwarding thing and the way sketches are often used for like hitting a normal, or like hitting some form or some invariance that happened, or you know cost will be low.
That's not a way we have thought about it, to be honest. But it would certainly make sense that like by trying to find the shortest and most efficient rewrite path, we will get something that is kind of in this, it lies in the space, that it's shorter and more direct. We kind of trade this off by how we slice up the training data, of course. If we take bigger jumps and take something in the middle, then of course there's more distance between that, and that's one dial we can tune. But at the moment, we are only taking very short jumps, which equate, of course, to more iterations that need to it may run. So no, but I think it's a good thing. Let's talk about it later.
Cool, great talk again. Yeah, sorry, Max.
It's okay. Now I'll ask my other question. One sort of difference between, at least what I understand of this approach, is you want to train your model on data that pertains to the domain that you're working on. Is that correct?
Yes, we have a domain-specific model for each language. Yes.
Yes. So is there an opportunity for sort of cross or pre-training, right? Like if I had one for a domain that was, similar-ish, like for example, a lot of domains have things about addition and multiplication and these commute and associate, right? So could I sort of take a pre-trained model and then augment it in my domain, but it has like, it's pre-trained on a sort of more generic domain?
So that's a decision we made not to do because we want to keep the size of the model small. And if we make it more general, then we need to increase the size of the model, which means we both need more training data and more compute, and we try to avoid it. And we try to follow the mode that we have a specific model that's good at only one thing, and that's why we can keep it small, especially because we don't want to run into the issue that, well, our equality saturation only takes 5 gigabytes of RAM, but we need 80 gigabytes or 320 gigabytes of language model to solve that, which kind of, well, I mean, you can do that trade-off, but then I don't think it's fair to say, no, my equality station doesn't take a lot of memory because it hides it in the model.
Thank you for the great talk again. So kind of building off that, or I guess similar, is so the model is trained on a language, or each domain's language, but then I guess similarly, the models, like the training data is dependent on the rewrites available, because whatever rewrites you have, you're going to generate like different guides. So, and then I guess like if you added in a rewrite now what a good guide is, your model would, basically I guess what is the interplay there of like, if I go and modify my rewrite set, how useful the model being able to predict the guides is?
So the model is definitely trained on the set of the language, the rewrites, and to some degree, most likely also on the scheduler. So this is baked in. Changing the language would just completely break the model. But adding one rewrite or another, well, you most likely won't make it that much worse, but the model isn't trained to take advantage of these, to generate clever sketches to take advantage of these rewrites. Then again, if you have a system where you regularly solve the same thing in the same language, in the same system of rewrites again and again, then I don't think that would be too much of an issue. But as it's now, you bake those rules into the model. Yes.
Yep. Thank you.
Okay, let's thank the speaker again. Okay, and our final talk will be Phil, and he's going to be changing gears a little bit to talk about EGRAPHS modular theories.
Okay. Maybe I do need a different dongle. Thank you. Oh boy. Yeah. Yep. Now just, sorry. To Berkeley. Wait, what is
I think they should be on. Yeah.
it's just a PDF. Sent it here. Okay, well, thank you all for coming. I want to start off, as every great talk starts off, with an apology, not for my technical issues here, but because I know you're all tired, it's been a long day,
You've seen a lot of great talks. And unfortunately, I have another great talk for you, okay? And I've got some really great ideas that get me really excited, a foaming foment. And I'm going to have to just squeeze a little more juice out of these shriveled brains you got. So here, what are we talking about today? Omelets need onions, eGraphs modulo theories via bottom-up e-matching. So what is the motivation? For this? As we've described multiple times today, AC sucks, right? Okay, so this is sort of the paradox of equality saturation, that one of the great things about equality saturation is that it deals with difficult to orient rules in a declarative way. And sort of canonical examples of difficult to orient rules really are associativity and commutativity, okay? But when you actually go and do this using equality saturation, the eGraph explodes. So here we have the example of x1 plus x2 and so on up to xn. If you fully equality saturate this with respect to the AC rules, you get an exponential number of e-classes, one e-class for every possible subset of those variables, and this thing grows and grows and grows and grows. Okay, but this creates like cognitive dissonance because this is crazy, right? This is what we're doing here doesn't seem that complicated. If I had a problem where I give you two terms, one of which is a reassociation and swapping and jumbling of the other term, if I use this generic method to do it, I'm doing like an exponential search. But the obvious thing to do is I should flatten the two terms, sort all the pieces inside of them, and then check if they're equal. It's a very fast, very simple thing to do. And I mean, it's awesome that equality saturation is this super simple generic mechanism that can handle all sorts of stuff you throw at it. But it's kind of crazy, it feels like, that you're paying all this cost for something that should be easy. Shouldn't it be easy? Okay, what can we do about that? That's the motivation for the idea of eGraphs modulo theories. Can we bake in domain-specific smarts into the eGraph, right? And not just AC. There's other things we might want. We might want polynomials. We might want linear expressions. We might want baked-in notions of sets. And we can encode all these things into the generic eGraph facilities. But we want baked-in notions that do smart stuff and are more efficient things. And there's a spiritual guide for what we're trying to do here that satisfiability modulo theories, SMT, is a super successful paradigm. And what it is it's a bunch of domain-specific smarts about particular theories that are tied together in the center by the fabric of a SAT solver and an eGraph, okay? And what we're doing, is very similar and inspired by a lot of the things that are happening in the SMT world. But we don't really need the SAT solver as much. We have a different problem we're sort of attacking. We're trying to do the simplification problem, the program optimization problem, whereas the SMT solver is really oriented to this backtracking SAT stuff that's happening, to proving things are unsat, to getting particular satisfiable models. So everything in there is engineered to that use case, and can we renegotiate what we're doing and re-emphasize, remix the data structures, remix these ideas. And these are just generic, these are ideas that have been around a long time and are put into a particular form in SMT solvers. But can we take the same sorts of ideas and come up with something reasonable that we can call eGraphs modulo theories? In particular, we want a super strong notion of e-matching because it's core to the equality saturation approach is that we're doing e-matching, where that's a little less central to the SMT approach. The central part of the SMT approach is ground stuff without the e-matcher. That's sort of a really nice thing put on top. But when you actually go to try and do this sort of thing, try and think about how could this make any sense at all, the massive eGraph sharing, the thing that makes the eGraph awesome, also makes it super confusing. How do you disentangle the pieces you need to disentangle to actually do this theory-specific reasoning? How do you reach deep down inside of stuff and do this? So it's okay, what do we do? I think there's a generic problem-solving strategy for when things are complicated. You simplify, you simplify, you simplify until basically it's obvious how you're going to do this thing. Then you start adding on complication, right? And I think it's important to note that the eGraph plays multiple roles. And what I want to show today is teasing apart these very distinct and I think very separable roles the eGraph is playing. And the equality saturation, the typical equality saturation algorithm, is a particular strategy for combining all these roles, but you can recombine them and use them in different ways. So in particular, eGraphs are term banks. They're things that offer ability to add terms into it, and they hold on to it somehow. They're a thing that you can find terms, or like produce a thing. You can give it a pattern of a sort of thing you're looking for, and then it'll return a list of substitutions of like the things that are in the graph that like match that pattern. And then also, crucially, there are quality stores. There are things that you can assert equalities into, and they hold those equalities and compact, you know, with respect to those equalities. So those are like the three main things that eGraphs do. Okay, so focusing on the first one, just adding terms into term banks. To simplify the problem significantly, like if we want eGraphs modulo theories, but just want to focus on adding terms, what we have is term banks modulo theories. Okay, and so how do we support a rigid baked-in notion of a nice theory in the context of a term bank, of an interning structure, a hash cons? And by nice theories, kind of what I'm alluding to is something that supplies a convergent set of rewrite rules, such that you can apply the rewrite rules or canonization procedure, a rigid baked-in canonization procedure that will give you a canonical form of something that isn't canonical. So it takes this funnel of stuff, and it'll give you the tip of the funnel, and it'll give you the same tip every time, no matter where you are in the starting funnel. And one methodology for doing this sort of thing is smart constructors. So here's a very simple example for baking in the notion of x plus 0 rewrites to x. Here's a smart constructor where, you know, it just checks if you gave it 0, and you know, it doesn't do, it just gives you back x if you did that. But otherwise, it actually does hash cons and creates a new thing inside of the term bank that you can search for, you're going to be able to search for later. And these smart constructors can have more complicated stuff in them. You'll have all sorts of things in them, and they can recursively call each other. And it's an approach that makes sense for like putting things, only the canonical forms, into a hash cons. Okay, so I mean that was a whirlwind, but that kind of gives us a check mark on the first thing. Like we can have a notion of term banks modulo theories. But now we want to think about matching. Like how are we going to do this part? And so the basic issue is that like we've destroyed all the things that were up in the funnel are actually the things we want to match on. And the only thing that's actually materialized inside of our data structures is the very tip of the funnel. Okay, so we have an example like a pattern, x plus 0, like that should match on everything, right? Because like everything is equal to x plus 0. And if we add this particular term, x plus 0 plus y, into our term bank, we'll get that thing inside of our term bank, and there's no zeros in there. So if you do a naive thing that's looking for zeros, a naive pattern matching, you're not going to find it, you're not going to match on anything. Okay? So I think there's a first intuitive thing that like, okay, well, we just need to like generalize what we're doing in matching. And really this is related to what even the e-matching is happening as inside an eGraph. And so instead of doing like this thing where we're doing just structural looking, every time we look down inside a node, we need to expand into that funnel and look for all the stuff that might work in that funnel as we're breaking into each of these nodes. And the way top-down e-matching works in the context of a term bank is the very first thing you do actually is you scan the entire term bank for a root to start top-down e-matching on. Okay? And then the number of substitutions you're going to get out of this thing depends on the particular theory we're talking about. And every time you go down a node inside of your pattern, you sort of gain a possible theory factor f of the number of substitutions. And these factors are multiplying as you go down the patterns. And we can talk about expanding these things out for multiple different theories. The thing that's like the baseline version of structural matching is like the theory of algebraic data types. You might call that. You might call it not having any theories. Maybe that's another perspective you might have. And the theory factor there, the thing that we're most used to talking about, the thing that happens in most programming languages, the theory factor is 1. But now we're really emphasizing like the equational case, the case where there's theories baked in. Okay, so one example of that is an eGraph where you have this enode pattern. You want to see if that enode pattern is inside of that e-class. So the size of that e-class is the number of possible branching factors that occurs as you traverse down into that pattern. There's multi-set patterns, and there's more than one notion of multi-set pattern, which I think is pretty interesting. And multisets are also interesting. I started talking about associativity and commutativity, and kind of multisets are a way of talking about associativity and commutativity. Multiset, an associative and commutative expression is a multiset of all the leaves that are in that expression. So multiset pattern notion 1 is that we have variables as elements inside of the multiset. And in that case, the number of variables we have inside that pattern, all permutations of that, is the theory factor as we go down there. There's a second notion of multiset pattern, which matches more of our notion of what we typically want when we're talking about AC matching, which is the multiset addition needs to match this other thing. And then the theory factor is the number of partitions, is the number of possibilities we'll get as we go down this thing. And then we get to something very interesting that really, I think, kind of just stops us in our tracks about like, what are we doing? Does what we're doing even make sense? And that's linear patterns, if I'm talking about linear arithmetic. And linear is supposed to mean good. It's supposed to be like the most tractable thing there is, right? And as I've phrased the problem so far, that you need to return like a list or a stream of substitutions of a particular kind, this actually has a theory factor of infinity. Like when you hit this thing, the solutions are x binds to any possible integer z, and then y would bind to any possible integer 42 minus c. And all of those possible combinations are valid substitutions to this problem. Okay, so it's like, what do we do at this point? Well, I guess we must have been asking for the wrong thing. The signature of match must have been wrong. Maybe we should return like a frozen constraint. Maybe we should like go somewhere else into the pattern, hopefully ground x first, and then this becomes like more tractable. You know, there are different possibilities, but I want to talk about a very interesting and like simple, like cutting the Gordian knot kind of possibility of how to deal with this problem. And that's the first key idea of this talk, which is bottom-up e-matching. And really, we've been talking about e-matching over the term bank, not on the term. We reduced in top-down e-matching the problem of matching over the term bank, this second signature, into this first thing, but we don't necessarily have to do that. A lot of our intuition about pattern matching comes from this single term case, which is what happens in most programming languages. And like, you know, people are just sort of used to thinking about like the one problem at a time, but it's very common, like vectorized thinking, or thinking in the context of like you're doing a bunch of things at once, is like changes how you look at an algorithm. And the algorithm is like brutally simple. Like there's almost no explanation to give because it's so simple. And really what you do is you bind variables by traversing the term bank. Like you decide the set of substitutions I want is ones where the variables are bound to something that was inside of the term bank. And in that case, there is like a maximal set of substitutions you could even want to return, a finite maximal set. And you can do this by a brute force like nested for loop thing. So here I have an example of the pattern foo bar of x, y. And in order to bottom-up match this thing, we just guess something for x. We traverse every possible term for x. We guess something for y. We guess every possible term for y. Then we can just look up inside of our term bank, or we can construct this canonized term of foo of bar of x, y, and get the left-hand side. And then the standard strategy in equality saturation is we prune what we consider to be useful equalities based on things that are related to an initial like important term by rewrites or the subterm relationship or combinations of rewrites in the subterm relationship. Because those are the things via congruence closure might like make something interesting happen to our initial target term. Okay, so we can check if it's in the term bank, and then we can construct the right-hand side, and we'll get to it. We can add the equality back into the eGraph. I'll just note this is the like it's as simple as it looks. Like it's kind of like I think the simplicity is sort of part of the greatness of it. And oop, okay, we're back. Maybe. But there are some optimizations you could put on top of this just to start mentioning a little bit of it. That bar of x doesn't depend on y. You could do early pruning by pushing that bar of x up above the for loop for y. You should also do pruning on what things you're expanding out of in terms. And like you should expand only out of the things that are of the sorts of the variables you're looking for, which is kind of a way of baking in the A-log tutorial yesterday, we're talking about this universe trick of keeping a table that's all the terms that are in a particular sort. Like this is sort of baked into this idea of how you're approaching the problem. And then also, if you can use the tables to sort of prune things that you want to do, this starts to push more and more towards the worst case optimal join style of doing things, just with a very particular ordering of what you're doing. So you can start optimizing in that sense towards the worst case optimal join version of this. But really the punchline here is that bottom-up E-matching plays much, much nicer with theories. Okay? And so to see this, we can talk about the rough asymptotic cost of these different procedures of going about it. The cost of top-down E-matching is you pay a cost T for scanning the entire term bank to find that root term to start top-down E-matching on. So you pay that no matter what. And then every time you expand a theory node, you pay the theory factor F. Okay? But for some theories, if you look at it this way, the theory factor F is infinite. It's just like not even doable. Or it's like some combinatorially large thing that involves a factorial or something. So this can be expensive for very, very deep patterns. The more you're traversing down into the patterns, the worse and worse this gets. Whereas bottom-up E-matching, you're doing this like backwards feeling thing on the outset of like an exponential cost in the number of variables of your pattern scanning over the entire term bank for each of these. So it's exponential in the size of the term bank and the number of variables in your pattern. But notice the theory factor doesn't even show up in this expression because you build a term, you canonize it, use your canonizer, and like you don't have to expand out these things according to the theory expander. And so it changes the incentive structure even of what you're trying to do. Now I paid this I've done this kind of horrible thing to like do this bottom-up E-matching thing, but now every theory I add in, you get the theory for free. It doesn't cost any implementation effort in terms of making a new expander. You have to make a canonizer, and you don't pay the theory factors of expansions when you're traversing down through patterns. And yeah, so a good example for top-down matching is, or a bad example for top-down matching is a very deep pattern with few variables. You're like paying that cost T no matter what, whereas in bottom-up E-matching pays the cost T to like bind to X, but then it just builds the thing. So that's like a good situation for bottom-up. A very bad situation for bottom-up is tons of variables in a very shallow pattern. That's like not a good situation for bottom-up, but a much better, good situation. You pay very few Fs for top-down. And really, of course, like the optimal versions of all these things are going to be mixes of all of it. It's going to be a relational style thing, or you're switching between top-down and bottom-up, or side-to-side. And that strategy has to be able to beat top-down and bottom-up because it includes both of them. But I think bottom-up is really interesting as a point on the Pareto frontier of simplicity and power. And the reason it is so simple and it I think kind of works so well is that bottom-up also grounds really, really fast. It immediately grounds the pattern, whereas top-down delays grounding the pattern as long as possible. Ground is good, unground is bad. That's like a lesson of EGRAPHS. EGRAPHS is all about ground terms. It's a lesson from term rewriting. Like all the ground stuff is way, way better behaved than anything with variables in it. And also, in terms of implementation effort, you only need the canonizer to do bottom-up. You don't need to implement a new thing in terms of the expander / unapply. Thank you, Max, for the pointer to the magic word unapply. OK, so we've discussed a version of term banks modular theories where we can add terms, we can match over them. And now I want to talk about the last component where you want to be able to assert new equalities. We only have this rigid notion of rewrites of theories and things. We want to be able to add in these things that we're learning online into the thing. And yeah, so we're sort of switching gears a little bit into a true eGraph style thing. So a question to ask, what does a union find really do? What interface does it present? So you have the union find T that stores all the information of the union find. You have the notion of an ID. And then the union find can tell you if two IDs are equal. It can give you a fresh ID. It can canonize IDs. You can assert equalities using the IDs back into the union find. But not only a union find presents this interface. The interior details of the union find from the perspective of the functioning of the eGraph are largely irrelevant. The fact that they're integer IDs doesn't really matter. The way if you implement it as ref cells versus as a vector arena or something, that doesn't matter. Mostly what really matters is this interface. Okay, so that brings us to the second key idea, structured EIDs. EIDs that aren't just bare integers anymore that don't mean anything. And alternative names for this, and I really just can't pick one of them because I like them for different reasons, is semantic EIDs / the really loaded term values, okay? And the reason a like thing that I keep coming back to like foment on is that I really do think EGRAPHS are well thought of, at least, as models, as like semantic things. And for, in particular, a partial logic with 2 forms you can assert into it, there's a notion of equality, but also a crucial part of the way we use an eGraph is really, it's like very meaningful whether something is in there or not, whether you like say this term exists or doesn't. So there's some sort of term existence assertion that I think is really like the best fit logic for what an eGraph actually is. Another way to see that eGraphs are models is if you take Z3 and you make uninterpreted functions in an uninterpreted sort, and you ask for a model after asserting a bunch of equality axioms, you'll get back this thing that really is kind of is the eGraph. It gives you a bunch of values and tables, and, but it totalizes them, and it doesn't give you the minimal model, which is the thing we kind of want in the equality saturation case. Okay, so we want to have structured EIDs. And what we're going to do is replace the union find with theory-specific extensible canonizers, some of which require a notion of rebuilding, like the eGraph itself. And when it does, the rebuilding very often has the flavor of a ground Knuth-Bendix completion. And ground Knuth-Bendix completions are fairly well behaved compared to the general Knuth-Bendix completion case. In particular, the stock union find can be thought of as uninterpreted values and atomic equations. That's the theory it supports, the theory of uninterpreted values, these things that have no structure to them. And another thing that structured EIDs lets you do is it merges the concepts of containers, primitives, and EIDs. These are notions in egglog where you can have I64s or something, and then but they have to be like totally separate from things that are unionable. But these things start to be able to talk to each other, which is, I think, a useful capability here. Another sort of mantra of the approach is that e-nodes are the like intern things, whereas structured EIDs are like the ephemeral things, the things that you're going to destroy, the things that don't need to be interned, and the things that you want to be able to sort of deeply introspect all at once. So that's again the flavor of the idea. And then I have a pile of examples of things that take this shape. Generalized union finds, these extensible theory canonizers. So the basic version of it, the simplest version of it, is a union find where you have an atomic / uninterpreted structure EIDs that just look like E sub 1. The next version of it that I think is pretty interesting is more like what a union find looks like in Prolog, where you can union like a EID to like a concrete entity, a concrete I64 or a concrete notion of constructor. And I think there is utility in teasing out, even though you can encode constructors as part of the general e-node facilities, I think it's useful to think of it separately because it's like very canonical when something becomes a constructor. It's like, and that immediately lets you talk about disequality. Once you know 2 things are constructors and different constructors, you know they're never going to be equal unless your theory is inconsistent. And so the way it works is when you have 2 EIDs that get unioned together, you do the regular union find stuff. If you have a primitive being unioned with an EID, the primitive has to win and become the root. And if you union 2 compatible constructors with each other, you resolve the union call by unification. You traverse into the children. And so this is a notion of having baked in unification. Something, again, you can encode as rules, but it bakes it into the eGraph as like, oh, this is something really important we actually want. Another notion, and this is, so the top 3 are sort of the cheapest things you can do that are really kind of easy to just like slot right in there, is the notion of a group action. You can attach every edge in a union find with a group action relating a child to its parent. And so an example of this is a structured EID. Here's the example of using the group of addition with the integers. So you can negate an integer, that's the inverse, and you can chain these things as you go up the union find. You can add 7 plus 3 plus 4 as you like keep traversing these edges to understand the relationship to the root. And then if you want to compare 2 things, the invertibility of the group is the thing that lets you turn the comparison to the roots to the comparison to the 2 leaves. And there's a talk I highly invite people to check out at the PLDI sessions where they call this a labeled union find, and they're using it for program analysis. And an interesting idea that they talk about there is the interaction of this thing with the lattice analyses on the EIDs themselves. So these can talk to each other and inform each other, which I think is a really interesting idea. Okay, next level up in complexity, a really cool thing you'd want is linear expressions, structured EIDs that are linear expressions. So now, like, the things that go in the EID slot are like linear combinations of these base EIDs. And the way you can canonize these things is Gaussian elimination / row echelon forms of matrices. I have an example in the preprint that goes into more detail on this. But if you do once you pick an ordering of your variables in linear algebra, you can make a row echelon form, and that can be seen as a canonizer of linear expressions. And it's sort of an interesting, like, reflective kind of thing. I find this too interesting to not note. I don't know what the point of it is, but ground terms themselves have a canonizer, EGRAPHS. And so your EIDs could themselves be ground terms. You assert them into an inner EGRAPH. You extract out a canonical form, and that's like the extensible canonizer you could have. I don't know, kind of interesting. Okay, so all these are decidable and cheap. Now we're getting to decidable and expensive. So these still terminate, but like you're paying something here. Starting to be kind of an intense computation you might be paying for. So polynomials also have a notion of an extensible canonizer, and that's the notion of a Grosvenor basis. And so this makes sense from the context of commutative algebra or something, that like if you have a bunch of polynomials that you set to 0, you can convert them into a new set of polynomials that easily lets you canonize other polynomial expressions. And it has some of the flavor, again, of a ground Nuthbank's completion, but with all the knowledge about rings just totally baked into the thing. Another very interesting example, getting back to AC, the start of the talk, is ground multisets as structured EIDs. And you can do ground multiset Nuth-Bendix completion. I think it's a pretty straightforward notion of Nuth-Bendix completion. And this is also related to the theory of integer programming in terms of these things called Graver and Hilbert bases, which are in turn related to Grosvenor bases. So it's all sort of in a similar mishmash. Another sort of crazy thing you can kind of do is have your structured EID be SMT terms themselves, and you can canonize them using SMT sweeping, where you just like scan through all sorts of stuff and make a ton of SMT queries asking if these two things are equal. And if they are, now you can like add it into a union find and like replace one with the other one everywhere you see it. Boolean expressions, sometimes you might want to bake in a notion of Booleans, like doing, again, equational rewriting over Boolean algebra axioms is kind of a goofy way of dealing with Booleans, but I mean, it's awesome that the generic facilities deal with it in this super uniform way. But, SAT solvers are amazing, BDDs are super powerful. I think ordered resolution also kind of can make this happen. I'm a little shakier on that part, but I think something does make sense there. Okay, and then we can get to really strong, like undecidable theories, which have capabilities that are really interesting and useful, but the rebuilding of the canonizer is not guaranteed to terminate, okay, or succeed. But there are some caveats there that, like, okay, you could just early stop the rebuilding. Like, in some sense, once it's become undecidable, it's almost as bad. It is as bad as the rules were in the first place. Like, we all used to the rules don't really terminate either. So maybe you do a little bit of rebuilding of this thing and consider it more like running some of the EQSAT rules, sort of in the same class of thing. But in any case, it might be really useful to bake in associativity, just A. Strange that A is like way more complicated, worse theory than AC, but it is. And that's strings. And string Nuth-Bendix completion with structured EIDs that are sequences of EIDs is a canonizer for that. And rebuilding is running string Nuth-Bendix completion. And I think this is particularly interesting for stateful computation, because stateful computation is about a sequence of things you do. It's not, you don't commute them, generally speaking. And we really want a baked-in notion of stateful computation. I think that's a really intriguing line of thought, or something that supports stateful computation. And then finally, like going all the way sort of a crazy end, like you're putting you could put full Nuth-Bendix completion inside as the rebuilder, as the union find, and then it's almost like what even is the point of the infrastructure of the eGraph outside of that? Because Nuth-Bendix completion is like a super powerful thing of itself. But this is almost, like a thing people want is like a principled way of dealing with destructive rewrite rules. And kind of Nuth-Bendix completion is the principled way of dealing with destructive rewrite rules. Like it's a saturation technology that can do like reducing computations that destroy uninteresting stuff, but like in a not in a complete way. And then if you let me, I mean, everything I guess is kind of speculate, crazy talk, but like this is some real crazy talk. So there's many things that have been talked about at previous eGraphs or in the community, and I think they kind of fit into this paradigm, but when I've actually tried to do it, I'm like not so sure. So slotted EIDs, I really like that idea. I think like an intrinsic support of variable binding that's principled is like really compelling. And I kind of think it might be something like this, an EID that like has the structure of a very shallow lambda around it. I kind of think that's the right sort of thing. And part of the slotted EID idea has a group union find in it, dealing with permutations of slots. So there's like, it's pretty close to some of these ideas. But when I've actually tried to reconcile them, I haven't actually been able to reconcile like these two things. Colored EIDs is you want a notion of context. So what if we had some notion of gamma attached to every EID? I think that kind of does fit into the general paradigm. Non-commutative rings, I just understand this thing less, but it is sort of a generalization of the Grosvenor basis thing and strings, really. And this is probably going to be super undecidable. And then there's towers of structured EIDs. All of these things are basically containers. And I said, like, oh, we put the integer, normal EIDs, like that's the thing they're containing. But you could start to think about like, well, I don't know, what if we just had containers of containers of containers, and then like it bottoms out at like the very base EID. But I think this notion kind of makes sense. I'm a little less sure, though. And then a really crazy idea is slotted multisets. I think there's a ground-Bendix completion procedure that kind of makes sense that combines ground multiset completion with like this slotted thing that sort of deals with the permutation symmetries of the slots. Some related work. This is not the only way to go about things. I think there's a lot of ways to go about things. But some related work to talk about is there's normalized rewriting. There's some papers by Marche from the 90s. And sometimes it feels like the term rewriting people just know everything. But like figuring out what they're saying is a research project unto itself, at least for me. Alt-ergo actually is an SMT solver with a baked-in notion of AC matching, which I think is very interesting. And there's papers about this AC matching technology. Kohler et al. Has like the very pragmatic and I think possibly extremely effective approach to an eGraph modulo theory, which is you extract a term, use your regular term stuff, you assert what you learned back in. Like maybe that's just the right way to go. It's like makes a lot of sense. I love the simplicity of it. Like it seems great. A different approach, like I made generalized EIDs, but another thing you could try and do is generalized E-nodes. Where instead of having an ordered children, like requiring that E-nodes have ordered children, they could have containers of children. They could have sets of children or multi-sets of children or extensible vectors of children. And that's sort of a different, it's like one-off way of like placing where you want your theory smarts. A thing I've been playing with in some recent blog posts is a brute force SMT eGraph, which is kind of related to the SMT sweeping idea. But it's not exactly built in exactly the same way as some of the ways I've described in this talk. And then I really invite people to check out Pavel's blog posts. He has some really interesting points connecting E-matching to quantifier elimination. I think there's some really interesting ideas in those blog posts. And yeah, so thank you. Again, there's still much to do. This is not meant to close the door by any means on eGraphs modulo theories. It's meant to open the door, open the discussion as like, what other things could we ask of our eGraphs? What other things could be like in there that we want? How would we use them? What would the interface of these things even look like? What should the interfaces be? I think that's the discussion. There's a preprint describing what I've described here and maybe a little bit more. There's a basic prototype of an eGraph modulo theories in my umbrella project, Knuckle Dragger. So there's like docs there, and you can try out a variation of an eGraph modulo theories. Again, different in some respects from what I've shown here, but it is definitely using bottom-up E-matching because like I just think that's a super simple approach and very nice. All right, so thank you.
All right, so we have gone a little bit over time, so I think we should maybe take the questions offline. I really do encourage you to ask Phil about this stuff. There's some really good ideas in here, and if you want to see his eyes light up, ask him about Knuckle Dragger. It's a very, very cool project. So yeah, let's take these discussions offline. And that does it for this year's eGraphs. Thank you all for coming. Thank you to Phil and the other presenters for making it such a great day. And yeah, let's continue all these conversations offline. Oh, should we take a picture? Yes. If you would like to be in the picture, and we'll take a group picture together.